Please like and subscribe. Have a good night. The Forgetful Paradox. Imagine waking up one morning with a strange realization. You know that at some point today, you're going to forget something important. Maybe it's your keys, an appointment, or a conversation you had yesterday. But here's the twist. If you already know you're going to forget, then isn't that the same as remembering? And if you do remember, then you never truly forgot in the first place. This is the Forgetful Paradox, a strange loop of memory that plays tricks on your mind. Forgetting something means it's gone from your thoughts, but if you know you'll forget, then part of you is still aware of it. So are you really forgetting, or are you just waiting for the moment when the memory slips away? It gets even weirder when you think about how memory works. Sometimes, the harder you try to remember something, the more it slips away. But the moment you stop thinking about it, the answer suddenly pops into your mind. It's like your brain is playing a game with itself, hiding memories only to reveal them when you least expect it. This paradox isn't just a fun mental puzzle. It reflects real challenges in neuroscience and psychology. Scientists still don't fully understand why some memories vanish while others stay sharp for years. And if forgetting is just the absence of remembering, then where do forgotten memories go? Are they lost forever, or are they simply waiting for the right trigger to return? It raises an even bigger question. If you can predict that you'll forget something, do you have the power to prevent it? Or is forgetting an unstoppable force, something that will always happen no matter how much you try to fight it? The missing dollar paradox. The missing dollar paradox is one of those simple little puzzles that mess with your brain the more you think about it. At first, it seems like basic math, but then something feels off. It goes like this. 3 friends check into a hotel room. The manager tells them it costs $30. So they each chip in $10, handing over a total of $30. Simple enough, right? But later, the manager realizes he made a mistake. The room actually costs only $25. So he gives $5 to the bellboy and tells him to return it to the guests. But the bellboy is sneaky. He figures he can't split $5 evenly among 3 people, so he decides to keep $2 for himself. That leaves $3, which he gives back to the guests, each person getting $1 back. Now here's where things get weird. Originally, each guest paid $10, but they got $1 back, so now they've only paid $9 each. That's 9 times 3, which equals $27. The bellboy kept $2. That makes $29, but wait, they originally paid $30. So where did the missing dollar go? The more you try to track it, the more it feels like something is vanishing right in front of your eyes. It's frustrating because all the numbers seem to add up, but at the same time, they don't. The missing dollar isn't really missing. The trick is in how the money is being counted. The guests actually paid $27 in total, $25 for the room, and $2 stolen by the bellboy. But the way the question is framed makes it seem like the $2 should be added to $27 instead of already being included in it. The paradox works because it plays with our natural way of thinking about money. We assume there should be a direct balance, but a small shift in perspective creates confusion. It's a reminder that sometimes our brains trust patterns that don't actually exist. And just like that, a single dollar disappears, not from reality, but from logic itself. The time traveler's grandfather paradox. The time traveler's grandfather paradox is one of the most famous thought experiments about time travel. It sounds like a simple story at first, but the more you think about it, the more impossible it becomes. Imagine this. You build a time machine, you step inside, set the dials, and travel back to a time before your grandfather had children. You find him, and for whatever reason, you prevent him from meeting your grandmother. Maybe you scare him away. Maybe you accidentally cause an accident. Either way, he never has kids. That means your father is never born. And if your father is never born, then neither are you. But wait, if you were never born, then how did you go back in time in the first place? How did you stop your grandfather if you never existed? The moment you prevent your own birth, you erase the very reason you traveled back in time at all. But if you were never there to change the past, then your grandfather must have lived his normal life, had kids, and eventually led to your birth again. This creates an endless loop where reality can't seem to decide what's true. This paradox exposes a deep problem with time travel. If the past can be changed, then certain changes make time itself impossible. Some believe this proves that time travel to the past can never happen because any real attempt would create contradictions like this. Others suggest that history is self-correcting. Maybe something always prevents you from changing key events. Some theories even propose parallel timelines, where changing the past creates an alternate reality, so you never erase yourself. You just move into a different version of history. Whatever the answer is, the grandfather paradox shows us that time isn't just a simple straight line. It's something far stranger, something that might be impossible to rewrite without breaking reality itself. The lottery winner's paradox. The lottery winner's paradox is a strange way of looking at probability and luck. Imagine a huge lottery with millions of players. The odds of winning are unbelievably small, almost impossible. If someone told you before the draw that you were going to win, you'd laugh. But then, against all logic, your numbers come up. You won. Now, think about what just happened. Before the draw, you had no real reason to believe you'd win. It was too unlikely. But after you win, it's 100% true that you were always going to win. The odds went from nearly impossible to completely certain just because it happened. Here's the paradox. If something is extremely unlikely, should you believe it won't happen? If you only believe in things that are likely, you would have never expected your own win. But you won, proving that even the most unlikely events sometimes happen. This paradox challenges the way we think about probability. We assume rare things won't happen to us, but someone, somewhere, will always experience the unexpected. Now, take this idea further. If something has a tiny chance of happening, does that mean it won't? If we dismiss things just because they're unlikely, we might ignore real possibilities. The lottery winner's paradox reminds us that even the rarest things don't mean impossible, and in the end, someone always wins the lottery. Why couldn't it be you? The unexpected hanging paradox. The unexpected hanging paradox is a strange puzzle that plays with logic and prediction. Imagine a judge sentences a prisoner to be hanged, but adds a twist. The execution will happen on a random weekday, and the prisoner won't know the day until the executioner arrives. The prisoner thinks carefully. If Friday morning comes and he's still alive, he must be hanged that day. But if he knows that, it can't be unexpected. So Friday is impossible. Now he looks at Thursday. Since Friday is ruled out, if he's alive by Thursday morning, the execution must happen that day. But if he figures that out, it's not a surprise either. One by one, he eliminates every day. He smiles, convinced the hanging can never happen. But then, on a random morning, the executioner arrives. The prisoner is completely shocked. The hanging was unexpected after all. So where did his logic fail? The paradox shows how reasoning can sometimes contradict reality. The prisoner was right in thinking he could predict the last possible day, but he forgot one thing: his own surprise. Just because he logically ruled out every option doesn't mean the real world follows his thinking. This paradox challenges how we deal with uncertainty. If we overanalyze, we might assume things are impossible just because they don't fit our expectations. But life, like the executioner, doesn't always follow our logic. The silent argument paradox. In a silent argument, no words, no gestures, just silence. One believes their silence proves they are right. The other thinks the same. But if neither speaks, how can either one win? The paradox is simple. If silence means victory, then both have won. But if both have won, then neither has actually proven anything. Arguments usually need words. People debate, explain, and defend their views. But here, silence is supposed to be the proof. It's a contradiction, winning an argument without actually making an argument. This paradox plays with the idea of logic itself. Can an argument exist without being spoken? If two people refuse to talk, are they proving something or just avoiding the fight? It reflects real-life conflicts. Some believe that staying silent in a debate shows confidence, that their truth is so obvious it doesn't need defending. But what if the other person believes the same? Silence, instead of proving anything, becomes meaningless. It's not logic, it's just stubbornness. In the end, the silent argument paradox exposes the flaw in refusing to engage. If two sides never speak, no one wins. They just sit there, waiting for proof that will never come. The two envelopes paradox. You sit at a table with two envelopes in front of you. One contains twice as much money as the other. You pick one at random, open it, and see $100 inside. Now, a question. Should you switch to the other envelope? At first, it seems like a fair choice. But then, logic starts twisting. If your envelope has the smaller amount, the other must have $200. But if yours is the larger one, the other only has $50. Since there was a 50-50 chance to begin with, some argue that switching gives you an expected gain. gain. The reasoning goes like this. If the other envelope has $200, you gain $100 by switching. If it has $50, you lose $50. The average of these two outcomes suggests switching is always the better option. But that doesn't make sense, because you could apply the same logic to any envelope, forever trapped in an endless loop of switching. The paradox reveals a flaw in how we think about probability. Expected value suggests one thing, but reality doesn't follow the same rules. It questions whether logic alone can always lead to the best decision. In the end, no matter which envelope you choose, you're left with the same dilemma, always wondering if you should have switched. The self-eating cake paradox. You walk into a bakery and see a perfect cake on the counter, but there's something strange about it. The baker tells you this cake is special. It's self-eating. Every time you take a bite, the cake magically regenerates to its original size. No matter how much you eat, it always remains whole. At first, it sounds like an endless supply of dessert, but then the paradox sets in. If the cake is self-eating, does it ever really lose any part of itself? And if it regenerates instantly, did you ever truly take a bite? The cake exists in a strange state. It is both eaten and uneaten at the same time. The paradox plays with the idea of identity and continuity. If something restores itself the moment it changes, does it ever really change at all? This connects to deep philosophical ideas, like the ship of Theseus. If a ship has every part replaced over time, is it still the same ship? Or consider the human body. Cells die and regenerate constantly. After years of replacement, are you still the same person? The self-eating cake may seem like a simple thought experiment, but it forces us to question what it means for something to exist, change, or remain the same. The omnipotence paradox. Imagine a being so powerful it can do anything. No limits, no restrictions, absolute omnipotence. But then a simple question breaks everything. Can this being create a rock so heavy that even it cannot lift it? If it can create the rock, then there is something it cannot do, lift it. But if it cannot create such a rock, then there is also something it cannot do, make the rock in the first place. Either way, the being is not truly omnipotent. This is the omnipotence paradox, a contradiction that challenges the very idea of unlimited power. It reveals a hidden problem in how we define omnipotence. Can true power exist without self-contradiction? Some argue that omnipotence means being able to do all that is logically possible. That would mean the paradox is meaningless. Asking for a rock too heavy to lift is like asking for a square circle. Others argue that real omnipotence must include the power to override logic itself, meaning the paradox should be solvable. This paradox has been debated for centuries in philosophy, religion, and even modern thought experiments. It forces us to ask, does power have limits, or is the problem in how we understand it? And if a being were truly beyond logic, would we even be able to comprehend its power at all? The self-refuting paradox. Some statements seem logical at first, but collapse the moment you think about them. Take this one. There are no absolute truths. If that statement is true, then it must also be false, because it itself would be an absolute truth. This is the self-refuting paradox, a trap where a claim destroys itself by its own logic. Think about someone saying, I cannot speak a single word in English, but they just did, or a sign that says, ignore this sign. The very act of reading and understanding it means you failed to ignore it. These contradictions expose hidden flaws in how we use language and logic. This paradox isn't just wordplay. It appears in serious debates about philosophy, science, and even politics. Imagine someone claiming nothing is knowable. But if that's true, then they somehow know that nothing is knowable, contradicting their own statement. Even in science, this paradox can appear. If someone says, science proves that nothing can be proven with certainty, then their claim is also uncertain. The very foundation of logic and reason is built on avoiding self-refuting statements. The self-refuting paradox forces us to be careful with absolute claims. It shows that sometimes the biggest flaw in an argument isn't hidden, it's right there in the words themselves. The ignorance paradox. Some say that the more you learn, the more you realize how little you actually know. But if that's true, then does gaining knowledge only make you more ignorant? This is the ignorance paradox, a strange contradiction that challenges how we think about wisdom and understanding. Imagine a child who knows nothing about the universe. They don't question black holes, quantum mechanics, or the meaning of life, because they don't even know these things exist. But as they grow older, they start learning. They hear about space, atoms, and the mysteries of time. Instead of feeling smarter, they feel overwhelmed. Every answer they find leads leads to even more questions. The more they learn, the more they realize how much is still unknown. This paradox doesn't just apply to individuals, it applies to all of human knowledge. Centuries ago, people thought they understood the world. The earth was flat, the stars were tiny lights in the sky, and sickness came from bad air. But as science advanced, those ideas crumbled. We learned the Earth is round, the stars are massive, and diseases come from microscopic organisms. But instead of bringing certainty, these discoveries only led to bigger mysteries. What is dark matter? What happens inside a black hole? What is consciousness? Each discovery expands the list of things we don't understand. It's like climbing a mountain. At the bottom, everything seems simple. As you climb higher, you see more of the landscape. But instead of reaching the top, you only find more peaks stretching endlessly into the sky. No matter how much we learn, the horizon of the unknown keeps moving further away. Philosophers and scientists have debated this paradox for centuries. Socrates famously said, "The only true wisdom is in knowing that you know nothing." It suggests that real intelligence isn't about having all the answers. It's about understanding that knowledge itself has no end. The moment you believe you know everything is the moment you stop learning. The backwards law paradox. You want to be happy, so you chase happiness. But the more you chase it, the further away it feels. You want to be confident, so you try to prove yourself, yet deep down, you still feel insecure. You want to relax, but the harder you try, the more anxious you become. This is the backwards law paradox. The idea that the more you strive for something, the less likely you are to achieve it. Imagine trying to fall asleep. You close your eyes, focus on your breathing, and tell yourself to relax. But the more you think about sleeping, the more awake you feel. Sleep isn't something you can force. It happens when you stop trying. The same applies to happiness. The harder you try to be happy, the more you notice what's missing. The more you chase success, the more you focus on how far you still have to go. This paradox appears everywhere in life. Swimmers who panic in deep water sink faster, but those who stop struggling and float stay safe. The more you demand love from someone, the more distant they become. The moment you stop trying to be cool is when people start seeing you that way. It's as if effort itself becomes the very thing that stops you from getting what you want. Philosophers and psychologists have explored this idea for centuries. Eastern philosophy teaches that true peace comes from letting go, not holding on. In Zen Buddhism, trying to be enlightened is the very thing that stops enlightenment. Even in modern psychology, acceptance-based therapy suggests that fighting negative emotions only makes them stronger. So what's the solution? Instead of forcing things, allow them to happen. Let go of the need to control everything. And ironically, life starts to flow in your favor. Maybe the key to happiness isn't in chasing it, but in realizing you never had to chase it at all. The invisible gorilla paradox. You're watching a group of people pass a basketball. Your task is simple. Count how many times they pass the ball. You focus, tracking every move, making sure you don't miss a single pass. The video ends, and you confidently give your answer. But then someone asks, "Did you see the gorilla?" You blink, confused. What gorilla? This is the invisible gorilla paradox, a psychological experiment that reveals a shocking truth. We often miss what's right in front of us. In the original experiment, a man in a full gorilla suit walks through the scene, stops, pounds his chest, and leaves. And yet, nearly half the participants don't see it. They're so focused on counting passes that their brain simply ignores the unexpected. This paradox exposes a flaw in how we perceive reality. We like to believe that we see the world as it is, that our senses give us an accurate picture of everything happening around us. But the truth is, our brains filter out information all the time. If something isn't part of what we expect to see, we might not notice it at all. This effect isn't just limited to a harmless experiment. It happens in real life constantly. Drivers fail to see motorcycles on the road. Witnesses to crimes misremember key details. Even in our daily conversations, we might miss obvious signs about how someone is feeling. The invisible gorilla paradox is unsettling because it forces us to ask, what else are we blind to? If something as obvious as a gorilla can disappear from our awareness, how much of reality are we unknowingly missing? The law of triviality paradox. A group of experts gathers to discuss the budget for a new nuclear power plant. The meeting starts with complex technical details, but soon the conversation shifts. Instead of debating the critical safety measures, they spend an hour arguing about the design of the staff bicycle shed. The cost of the shed is almost nothing compared to the entire project, yet it gets the most attention. This is how important decisions get lost in trivial details. People tend to focus on what they understand, avoiding the difficult and abstract. Discussing nuclear physics is intimidating, but everyone has an opinion on a bike shed. The result? The least important parts of a project often get the most discussion, while critical issues go ignored. The law of triviality paradox appears everywhere. In business meetings, employees might spend hours debating the color of a new logo while ignoring major financial problems. In politics, people argue over minor policies while larger crises remain unresolved. The easier a topic is to grasp, the more debate it attracts, even if it barely matters. It's an uncomfortable truth. People avoid complexity, and that means sometimes the biggest problems, the ones that really need attention, are the ones most likely to be ignored. The Sleeping Beauty paradox. Sleeping Beauty volunteers for an experiment. On Sunday, she's put to sleep. A fair coin is flipped. If it lands heads, she is woken up on Monday, then put back to sleep, and the experiment ends. If it lands tails, she is woken up on both Monday and Tuesday, but each time her memory is erased, so she doesn't remember waking up before. Now imagine she wakes up. She has no idea what day it is or how the coin landed. If you ask her, what's the probability that the coin landed heads? What should she say? At first, the answer seems obvious. 50% since it was a fair coin flip. But here's the problem. If it landed tails, she wakes up twice, meaning she experiences two different moments of consciousness. If it landed heads, she only wakes up once. This makes her twice as likely to be in a tails scenario than a heads one. Some argue the probability should be 1/3 for heads and 2/3 for tails. Others disagree, saying the original 50-50 chance never changed, and that erasing her memory doesn't create a new probability. The debate continues, not just in philosophy, but in probability theory itself. It raises deep questions about knowledge, memory, and what it even means to assign probabilities when our own experience is uncertain. The bystander effect paradox. A man collapses in the middle of a busy street. Dozens of people walk by. Some glance at him. Others hesitate but keep moving. No one stops to help, not because they don't care, but because they assume someone else will. The more people around, the less likely anyone is to act. This is the bystander effect, a strange paradox of human behavior where responsibility is shared so thinly that no one takes it. Psychologists first studied this after the infamous case of Kitty Genovese, a woman attacked in New York, while dozens of neighbors reportedly heard her screams but didn't call the police. Studies confirmed that as group size increases, individual responsibility decreases. Each person thinks someone else will handle it, but if everyone thinks that way, no one does. Now here's the paradox. If one person sees someone in danger, they almost always help, but add more people and the chances drop. You'd think more witnesses would mean a higher chance of intervention, but the opposite happens. Responsibility dissolves, spread too thin to move anyone to action. It makes us question morality. Do people truly care, or do they only act when forced to? The bystander effect reveals a flaw in our instincts, a reminder that sometimes stepping forward requires overcoming the very logic that holds us back. The ship of Theseus paradox. A man owns an old wooden ship. Over the years, its planks rot and are replaced one by one. Decades later, not a single original piece remains. But here's the question. Is it still the same ship? This is the ship of Theseus paradox, an ancient puzzle about identity and change. If replacing parts doesn't change what something is, then the ship remains the same. But if identity depends on its original materials, then at some point, it stopped being the same ship. Now let's take it further. Imagine someone gathers all the old discarded planks and rebuilds the ship exactly as it was. Now we have two ships, one made of new materials but with continuous history, and one made of old materials but reconstructed later. Which one is the real ship of Theseus? This paradox extends beyond ships. What about people? Your body constantly replaces cells. After years, none of the original ones remain. Are you still the same person? And what about objects, traditions, or even nations? If everything changes gradually, at what point does it become something new? The paradox has no simple answer. It forces us to question how we define identity, not just in things, but in ourselves. Is something the sum of its parts, or is identity something deeper, something that persists even as everything changes? The Bootstrap paradox. A man finds a book filled with beautiful poems. Inspired, he copies them word for word and publishes them as his own. Years later, someone else finds his book, copies it, and republishes it again. This cycle repeats for centuries, until one day, the original book resurfaces. But here's the question. Who actually wrote the poems in the first place? This is the Bootstrap paradox, a strange loop where something exists without ever being created. It's a paradox of time travel, where information, objects, or even people seem to come from nowhere Imagine a scientist receives detailed blueprints for a time machine from a visitor claiming to be his future self. He builds the machine, travels back in time, and gives the same blueprints to his past self. But if the blueprints were never originally designed, where did they come from? It's a paradox because every event seems to depend on another without an actual starting point. In stories, musicians get famous by hearing their future selves play a song and copying it. A writer publishes a book they found in the past. The information moves in an endless loop with no clear beginning. The problem is, for something to exist, it must be created at some point. But in the Bootstrap paradox, that never happens. It simply exists. It challenges our understanding of cause and effect, suggesting that maybe, just maybe, time isn't as linear as we think. The reversed probability paradox. A doctor tells you that you've tested positive for a rare disease. You panic, but then you remember something about false positives. The test is 99% accurate, meaning it correctly identifies the disease 99% of the time. That sounds reliable until you ask a deeper question. What are the actual chances you have the disease? This is the reversed probability paradox, also known as the base rate fallacy. People assume that if a test is highly accurate, a positive result must mean they almost certainly have the condition, but probability doesn't work that way. Imagine only 1 in 10,000 people actually have the disease. That means out of 10,000 tests, 1 real case will be caught, but so will around 100 false positives. So if you test positive, you're actually much more likely to be one of those false positives rather than the single real case. This paradox plays out in all kinds of situations. A security system that's 99% accurate in detecting criminals might still flag thousands of innocent people just because true criminals are so rare. A spam filter with a 95% accuracy rate might still block plenty of important emails. The problem is that our brains focus on the test's accuracy and ignore how rare the actual event is. It's a mind trick that fools even experts, leading to wrong decisions in medicine, law, and security. The lesson? Just because something seems mathematically certain doesn't mean it actually is. The St. Petersburg paradox. You're offered a simple game. A fair coin is flipped until it lands on tails. If it lands on tails on the first flip, you get $2. If it lands on tails on the second flip, you get $4. If it takes 3 flips, you get $8. The payout keeps doubling. It's $16, $32, $64, potentially forever. Now here's the catch. It costs money to play, and you must decide how much you'd be willing to pay for a single round. Logically, you should pay a huge amount. If you calculate the expected value, the average winnings over many games, it comes out to infinity. Theoretically, no price should be too high, but in reality, almost no one would pay more than $10 or $20. That's the St. Petersburg paradox. It exposes a gap between mathematical logic and human decision-making. Why does this happen? One reason is diminishing returns. Winning $1 million sounds great, but the difference between $1 and $2 million doesn't feel as life-changing as the difference between $10 and $20. Psychologically, each additional doubling of money matters less and less. Another reason is practicality. No casino could actually pay out infinite money, and most people don't think in terms of endless possibilities. This paradox highlights a fundamental issue in economics and probability. Even when the math suggests an obvious choice, human psychology and real-world limits complicate the decision. So the next time you face a bet that looks too good to be true, ask yourself, is the value real, or is it just an illusion created by numbers? The Sorites paradox. You have a single grain of sand. Clearly that's not a heap. Add another grain. Still not a heap. Keep adding one by one. At what exact point does it become a heap? Is it 10 grains? 100? 1,000? The problem is, no single grain makes the difference. Yet at some point, a heap must form. Now let's go the other way. Start with a heap of sand and remove 1 grain. It's still a heap, right? Remove another and another. At what moment does it stop being a heap? There's no clear cutoff, yet eventually you're left with just 1 grain. Definitely not a heap. This is the Sorites paradox, an ancient puzzle that exposes the problem of vague definitions. Words like heap, bald, or tall seem clear, but they don't have strict boundaries. How many hairs make someone bald? How many inches make someone tall? Philosophers struggle with this. One response is to accept that some concepts have no precise borders. Another is the idea of sharp cutoffs. Some hidden point exists where change happens, even if we can't pinpoint it. But that feels unnatural. Some suggest redefining words with clear rules, but that strips away the flexibility of language. This paradox isn't just about words. It applies to law, medicine, and identity. At what point does a person become rich? When does life begin or end? If we can't define these things precisely, how do we make fair decisions? The Sorites paradox forces us to confront the blurry edges of reality itself. The Dunning-Kruger paradox. You've probably met someone who confidently explains a topic they barely understand. They speak with certainty, but their knowledge is shallow. Meanwhile, true experts often doubt themselves, questioning if they know enough. This strange reversal is at the heart of the Dunning-Kruger paradox. It starts with a simple idea. People with low ability tend to overestimate themselves, while those with high ability underestimate themselves. But here's the twist. If someone is too unskilled to recognize their own ignorance, how can they ever learn they're wrong? If they don't know what they don't know, they stay trapped in their illusion of competence. On the other hand, experts know so much that they become aware of how much more there is to learn. The more they understand, the more they realize their own limitations. This leads to a paradox. The least knowledgeable think they know the most, while the most knowledgeable feel they know the least. This paradox appears everywhere, in politics, science, business. The loudest voices in a debate are often the least informed, while those who hesitate to speak may be the true experts. The internet amplifies the problem. Anyone can sound authoritative online, spreading misinformation with confidence. Meanwhile, real experts, who carefully weigh their words, struggle to be heard. So how do we escape this paradox? The first step is humility. Recognizing our own blind spots allows us to keep learning. True intelligence isn't about knowing everything. It's about understanding how much you don't know. The real question is, are you aware of your own ignorance, or are you trapped in the illusion of knowledge? The double spending paradox. Imagine you have a single $10 bill. You go to a coffee shop, hand over the bill, and get your coffee. The money is now with the cashier. You can't spend it again. Simple, right? But what if that bill wasn't physical? What if it was digital? This is where the double spending paradox begins. In the digital world, information can be copied perfectly. A song, a document, a video, once it exists, it can be duplicated endlessly. Now apply that to money. If digital money is just data, what's stopping someone from copying it and spending the same dollar twice? Unlike physical cash, which can only exist in one place at a time, digital money has no natural restrictions. This paradox was a major problem for early digital currencies. If money can be copied and spent multiple times, it loses all value. Traditional banking systems solve this by keeping central ledgers. Every transaction is verified and recorded, but this relies on banks and governments, requiring trust in centralized authorities. Then came Bitcoin, which claimed to solve the paradox in a new way. Instead of a central authority, it introduced blockchain, a public, decentralized ledger. Every transaction is recorded, and once confirmed, it's irreversible. This prevents the same coin from being spent twice, solving the paradox through technology rather than trust. But does this truly fix the problem, or does it just shift the paradox to something else, like the issue of energy consumption, transaction speed, or security risks? The paradox may be solved in one way, but it raises new questions. In the digital age, can money ever be truly uncopyable? The hindsight bias paradox. You hear about a big event, a shocking election result, a market crash, or even a sports upset, and immediately a thought creeps in. I knew this was going to happen. It feels obvious in hindsight, like the outcome was always clear. But was it? This is the hindsight bias paradox, the strange way our minds rewrite history. Before an event, uncertainty looms. Multiple outcomes seem possible. But after it happens, our brains reconstruct the past to make it seem inevitable. We forget how uncertain we actually were. This paradox isn't just about memory, it warps how we learn. If we think we always knew it all along, we don't analyze what actually led to the outcome. We dismiss randomness, overestimate our own foresight, and underestimate luck. This bias affects everything: science, politics, even personal decisions. Doctors might misjudge past diagnoses, believing the correct answer was more obvious than it was. Investors convince themselves they always saw a crash coming, though they made no moves to avoid it. And in history, major events feel like they couldn't have played out any other way, even though countless alternatives once existed. The paradox is this: the clearer the past seems, the less we truly understand it. And if we always believe we knew it all along, are we actually learning from history or just rewriting it? The quantum superposition paradox. A cat sits inside a sealed box. Inside, there's a device that could release poison based on the decay of a radioactive atom. According to quantum mechanics, until you open the box, the cat is both alive and dead at the same time. This is Schrödinger's cat, the most famous example of the quantum superposition paradox. At the heart of quantum physics is a strange rule. Particles don't exist in one definite state until they are observed. Instead, they exist in multiple states at once, a concept called superposition. An electron, for example, can be spinning both clockwise and counterclockwise at the same time until it's measured. The moment we observe it, the superposition collapses and the electron chooses a single state. But what does it mean to observe something? Is it human consciousness that forces the decision, or does the universe itself resolve the uncertainty? This paradox challenges our fundamental understanding of reality. If particles can exist in multiple states, could entire worlds split based on different outcomes? Some physicists suggest that each possibility plays out in a separate parallel universe. Others argue that we simply don't understand the nature of measurement. Either way, quantum superposition suggests something deeply unsettling. Reality isn't fixed. It waits for an observer to decide what it is. But if observation shapes reality, then the biggest question is, who or what is doing the observing? The infinite monkey theorem paradox. A monkey sits at a typewriter, randomly hitting keys. It's nonsense, just gibberish. But what if it keeps typing forever? The infinite monkey theorem suggests that given infinite time, the monkey will eventually produce the complete works of Shakespeare, word for word, purely by chance. At first, it sounds absurd. Random typing should never create meaningful writing, right? But mathematically, the probability is never zero. The key idea is infinity. If the monkey has endless time, every possible combination of letters must eventually appear. Not just Shakespeare, every book ever written, every speech, every thought you've ever had, all randomly generated somewhere in the chaos. But here's the paradox. Even though it's mathematically possible, it's so improbable that it might as well be impossible. The universe itself may not last long enough for even a single coherent sentence to emerge. This paradox raises deep questions about probability and order. If enough randomness can create meaning, does that mean everything around us is just a rare pattern in the chaos? Some even link it to the origins of life or the idea of infinite parallel universes. If a monkey can type Shakespeare by accident, what does that say about the universe itself? Maybe, in an infinite timeline, even the most impossible things are just waiting to happen. The paradox of free will. You wake up in the morning and decide what to wear. It feels like a choice. Blue shirt or red shirt, coffee or tea. But was it really a choice? The paradox of free will questions whether we truly make decisions or if everything is predetermined. Imagine a world where every action is the result of past causes, your thoughts, experiences, and even the structure of your brain. If everything follows a chain of cause and effect, then every decision you make was set in motion long before you were even born. That would mean free will is an illusion. But if our choices aren't determined by past events, then what are they based on? Randomness? If choices are truly random, then they aren't really choices at all. This creates a paradox. If our decisions are determined, we aren't truly free. But if they're random, we still aren't in control. So where does free will fit in? Some philosophers argue that even if our choices are influenced by the past, we still experience them as real. Others say free will and determinism can coexist, that making decisions feels free, even if the outcome was always inevitable. But here's the real question. When you picked your shirt this morning, was it really your choice, or was the decision made for you before you ever realized it? The choice paradox. You walk into an ice cream shop, craving something sweet. The menu has two options, chocolate or vanilla. Simple. You quickly decide. But now imagine the menu expands to 10 flavors. Suddenly, it takes longer to choose. What about 20 flavors? 50? Instead of feeling excited, you start feeling overwhelmed. This is the choice paradox. The idea that more choices don't always lead to more satisfaction. It seems logical that more options mean better decisions. But studies show that when faced with too many choices, people freeze up. They spend more time deciding, feel less satisfied with their final pick, and often regret not choosing something else. It's called decision paralysis. Instead of feeling empowered, we get stuck in the fear of making the wrong choice. This paradox affects everything from shopping to relationships to careers. Too many choices can lead to anxiety, not freedom. That's why some of the happiest people simplify their lives, limiting their options to focus on what really matters. So next time you're stuck in a loop of endless choices, ask yourself, is more really better, or is it just making life harder? The arrow of time paradox. An egg cracks, the yolk spills, and no matter how long you wait, it never uncracks. A teacup shatters, but you never see the pieces jump back together. Time moves forward, always forward. But why? The laws of physics don't actually demand it. If you look at the equations that govern the universe, they work the same whether time moves forward or backward. Yet in reality, we only experience time in one direction. This is that arrow of time paradox. The reason, scientists believe, lies in entropy, the tendency of things to move from order to disorder. Imagine a deck of cards neatly stacked in order. Shuffle them, and they become a chaotic mess. But if you keep shuffling, they won't magically return to perfect order. That's entropy. It always increases, and it's the only law in physics that gives time a direction. But here's the real paradox. If the universe started in a highly ordered state, the Big Bang, then why? Why was it so ordered to begin with? If time can, in theory, move both ways, why do we only remember the past but never the future? Some physicists believe there could be another universe on the other side of the Big Bang, where time runs in reverse. Others think we simply don't understand time at all. Whatever the truth, one thing is certain. We are trapped in the flow of time, moving forward even if the universe doesn't tell us why. The immortality paradox. A man wishes for immortality. He dreams of endless years, watching civilizations rise and fall, gaining infinite knowledge. But then the centuries pass. His loved ones grow old and fade away. New generations come and go, yet he remains. At first, he embraces it. But as time stretches into millennia, a new question arises. Is living forever truly a gift, or is it a curse? This is the immortality paradox. At first, it seems like an easy answer. Who wouldn't want more time? Time to learn, to explore, to experience everything the universe has to offer. But then reality sets in. The world changes, but the immortal does not. Loneliness grows, boredom creeps in, even the greatest wonders lose their magic when there is no end in sight. And here's the paradox. If life has no end, does it still have meaning? Some argue that life is precious because it is temporary, that without death, nothing truly matters. Challenges lose their weight, choices become meaningless. Others say that an immortal could keep reinventing themselves, finding new purpose forever. But what happens after 1,000,000,000 years, or 1,000,000,000,000? Would the mind eventually collapse under the weight of eternity? The paradox is simple. The very thing that makes life valuable, its limited nature, disappears with immortality. And if nothing is rare, can anything truly be precious? The lottery ticket paradox. A man holds a lottery ticket. He knows the odds, 1 in millions. He tells himself there's no chance he'll win. After all, almost every ticket is a losing one. But then he stops and thinks, if every ticket holder believes their ticket won't win, then by that logic, no ticket should ever win. And yet, every lottery has a winner. This is the lottery ticket paradox. It's a strange contradiction. Individually, it's reasonable to say any single ticket will lose. The probability is overwhelmingly against it. But when you apply that reasoning to every ticket, it leads to an impossible conclusion. No one should ever win, even though someone always does. It's a failure of logic when dealing with probability. The paradox highlights how our understanding of certainty and belief breaks down with large numbers. Just because something is extremely unlikely doesn't mean it's impossible. Yet the human mind struggles with probability in this way all the time. We dismiss rare events as impossible and assume likely events as guaranteed. But in reality, probability doesn't work like that. So if someone tells you there's no way you'll win the lottery, they're probably right. But if they say no one will win, they're definitely wrong. The inconsistent truth paradox. Imagine a book that contains only true statements. Every sentence in it has been carefully verified, but then someone adds a new sentence. At least one statement in this book is false. Now the whole system collapses. If the sentence is true, then there must be a false statement in the book. But if it's false, then every statement in the book must be true, including the one claiming there's a false statement. Logic folds in on itself, and the truth becomes impossible to pin down. This is the inconsistent truth paradox, where a system built entirely on truth contradicts itself the moment a certain kind of self-referential statement is introduced. It's similar to the famous liar paradox, but expands beyond just language. It questions whether absolute truth can exist in a system that allows contradictions. Mathematics, philosophy, and even legal systems wrestle with versions of this paradox. Can a system ever be both complete and consistent? Gödel's incompleteness theorem suggests that in any complex enough system, there will always be truths that cannot be proven within that system. The paradox forces us to ask, is truth something we can fully define, or is it always just out of reach? And if a simple sentence can make truth unstable, how much of what we believe to be certain is actually built on shaky ground? The energy drain paradox. You sit down after a long day, exhausted. You know you need rest, but here's the problem. You're too tired to sleep. Your body is drained, but your mind won't shut off. The more you think about how tired you are, the harder it is to relax. It's as if the energy you need to sleep is the very thing you no longer have. This is the energy drain paradox. When you push yourself too hard, your body and mind become so depleted that they struggle to do the one thing that could actually help: recover. Is the same reason overworked people find it difficult to unwind, or why burnout makes simple tasks feel impossible. Rest requires energy, but exhaustion takes away the ability to recharge. The paradox extends beyond just sleep. Athletes who overtrain become too fatigued to improve. Students who cram for hours absorb less information. Even in social situations, people who are emotionally drained struggle to connect, even though human interaction might be what they need most. So how do you escape? The answer is counterintuitive. Stop forcing it. The more you try to relax, the harder it gets. But when you let go, rest comes naturally. The energy drain paradox is a reminder that sometimes the best way to recover isn't by doing more, it's by allowing yourself to do nothing at all. The observer's paradox. You walk into a quiet cafe, looking for the perfect spot to observe people. You sit down unnoticed and watch as the scene unfolds naturally. But the moment someone realizes they're being watched, everything changes. They adjust their posture, speak differently, act more carefully. The normal, unfiltered reality you wanted to observe is gone. Your presence has altered it. This is the observer's paradox. The very act of observing something can change what's being observed. It happens in science, where researchers struggle to study people without influencing their behavior. It happens in nature, where animals act differently when they sense human presence. It even happens in everyday life. Think about how your voice changes when you know you're being recorded. The paradox becomes even stranger in physics. In quantum mechanics, particles exist in multiple states until they're measured. The moment they're observed, they choose a single state. Reality itself shifts just because someone is watching. So can anything ever be truly observed as it is? Or does awareness always distort reality? The observer's paradox reminds us that the line between watching and influencing is thinner than we think. Sometimes, just by looking, we change what we see. The algorithmic randomness paradox. You flip a coin over and over, writing down the results. Heads, tails, heads, heads. No pattern, just randomness. But what if someone asked you to write down a truly random sequence instead of flipping a coin? Could you do it? Strangely, the answer is no. This is the algorithmic randomness paradox. True randomness means no hidden order, no way to compress the information into a simpler form. If a sequence can be generated by a short set of rules, then it's not truly random. It has structure. But here's the problem. If something is truly random, there's no way to prove it. Any sequence of numbers might seem random, but how do you know it isn't following some deeper, unknown pattern? Computers face this issue all the time. They generate random numbers using algorithms, but because an algorithm follows rules, the numbers aren't truly random. They only appear that way. Even nature, with its chaotic storms and rolling dice, might not be producing true randomness, just complexity beyond human understanding. So is anything actually random, or is randomness just an illusion of ignorance? If something is so unpredictable that no pattern can be found, does that mean there's no pattern at all, or just that we haven't discovered it yet? The Doppler dilemma paradox. You're standing on a sidewalk when an ambulance speeds past. As it approaches, the siren is loud and high-pitched, but the moment it passes, the pitch suddenly drops. This is the Doppler effect, how sound waves compress when something moves toward you and stretch when it moves away. But here's where things get strange. Imagine a futuristic spaceship moving at nearly the speed of light. If it emits a sound or even a light signal, the waves in front of it get squeezed into higher frequencies, while those behind stretch out into lower ones. Now suppose two identical spaceships are moving toward each other at near light speed. From each pilot's perspective, the other ship's signals should be incredibly compressed, almost infinitely high in frequency. But each pilot would also see themselves as stationary and the other ship as the one moving. This means both should experience extreme frequency shifts in opposite directions. But how can both be true at once? The paradox emerges because relativity complicates how motion and time interact. As objects move faster, their perception of time slows down, changing how they experience waves and signals. The Doppler dilemma forces us to question whether frequency shifts are absolute or just an illusion of perspective. If motion changes reality itself, how do we ever know what's truly happening? The hole in reality paradox. Imagine you're holding a donut, not for the taste, but for the hole in the middle. That hole isn't made of anything. It's just empty space, defined only by the donut around it. But here's the question. Does the hole exist? If you take a bite, the shape changes, but the hole is still there, just in a different form. If you eat the entire donut, the hole disappears. But how can something that never physically existed suddenly be gone? This is the hole in reality paradox. The idea that some things seem real, but have no actual substance. We name them, describe them, and even measure them, yet they don't truly exist on their own. A black hole is another example. It's defined by an absence, an empty void where even light can't escape. But can something made of nothing actually be real? This paradox challenges how we define existence. If something is only defined by what surrounds it, does it have an independent reality? Consider shadows, silence, or even time itself. They only make sense in contrast to something else. But if nothingness can be real, then what exactly is reality made of? And if some things exist only because of our perception, how much of the world around us is just an illusion? The Zeno's motion paradox. Imagine you're in a race, running toward the finish line, but before you can reach it, you must first get halfway there. Then you must cover half of the remaining distance, then half of that, and so on forever. No matter how small the distance gets, there will always be another halfway point to cross. If you keep dividing the distance, you'll have an infinite number of steps to take. So how can you ever reach the finish line? This is Zeno's motion paradox, a puzzle from ancient Greece that seems to prove motion is impossible. If space is infinitely divisible, then reaching any destination would require completing an infinite number of steps in a finite amount of time. That sounds absurd. After all, people finish races every day. But mathematically, the logic seems airtight. The paradox forces us to question how motion truly works. In reality, we move continuously, not in separate, frozen moments. But Zeno's reasoning challenges the idea that space and time are smooth. Modern physics suggests that on the smallest scale, space and time might not be infinitely divisible. They might come in tiny, indivisible units. If true, this could mean that Zeno's paradox isn't just a trick of logic, but a clue to the nature of reality itself. So the question remains, is motion truly continuous, or is reality made of tiny, discrete steps we just can't see? The infinite regression paradox. You're standing in front of a mirror, holding another mirror in your hand. You tilt it just right, and suddenly you see an endless tunnel of reflections stretching into infinity. Each mirror reflects the other, creating an image within an image, forever repeating. But here's the question, where does it actually end? This is the infinite regression paradox, where an explanation or process keeps relying on something else before it, creating an endless chain with no starting point. Imagine asking who created the universe. Someone might say God created it. But then you ask who created God? And if there's an answer to that, you can ask, and who created that? No matter what, the chain keeps going forever with no final answer. It appears everywhere. If a king has authority, who gave it to him? And who gave them that authority? If knowledge comes from proof, then what proves the proof? In philosophy, it's called the problem of the unmoved mover. There must be a first cause, but finding it seems impossible. One way to escape is to assume something exists without needing an explanation, like an axiom in math or a fundamental force in physics. But even then, the question lingers. Why that and not something else? The paradox exposes the limits of how we understand cause and effect. If every answer depends on a previous one, how do we ever get to the ultimate truth? Or is reality built on something we'll never truly explain? The Maxwell's demon paradox. Imagine a tiny, invisible being standing between two rooms filled with gas. This creature, known as Maxwell's demon, has one simple job: opening and closing a small door between the rooms. But it's not just any door. The demon lets only fast-moving particles pass in one direction and slow-moving particles in the other. Over time, one room gets hotter while the other gets colder, creating a temperature difference without any external energy. This seems to violate the second law of thermodynamics, which states that entropy, disorder, must always increase in a closed system. If Maxwell's demon really worked, it could create a perpetual motion machine, producing unlimited energy without any effort. But there's a problem. Even if the demon doesn't move, it still has to observe, decide, and act. That process requires information, and processing information takes energy. In the end, the demon itself must generate entropy by making decisions, canceling out any benefit it might have created. The paradox highlights the deep connection between energies and information. In modern physics, it helped reveal the role of computation in thermodynamics. It turns out that even an all-knowing demon can't break the fundamental laws of nature. The universe doesn't allow shortcuts. Every gain must be paid for somewhere else. The black hole firewall paradox. Black holes are mysterious enough on their own, but they become even stranger when you consider what happens at the event horizon, the invisible boundary where nothing can escape. According to general relativity, if you fell into a black hole, you wouldn't notice crossing the event horizon. You'd simply drift past, feeling the pull of gravity as space bends around you. But quantum mechanics tells a different story. It suggests that the event horizon might not be smooth at all. Instead, it could be a wall of high-energy radiation, a firewall that incinerates anything that tries to cross. Black holes are mysterious enough on their own, but they become even stranger when you consider what happens at the event horizon, the invisible boundary where nothing can escape. According to general relativity, if you fell into a black hole, you wouldn't notice crossing the event horizon. You'd simply drift past, feeling the pull of gravity as space bends around you. But quantum mechanics tells a different story. It suggests that the event horizon might not be smooth at all. Instead, it could be a wall of high-energy radiation, a firewall that incinerates anything that tries to cross. This is the black hole firewall paradox. If firewalls exist, they violate the principle of relativity, which says falling into a black hole should feel no different than floating through space. If they don't exist, then another fundamental rule, the idea that information cannot be lost, must be broken. Physicists are stuck between these two impossible choices. Either Einstein's equations don't fully describe black holes, or quantum mechanics needs a major rewrite. Some propose that information somehow escapes the black hole, avoiding destruction altogether. Others think black holes might not be what we imagine at all. Until we solve this paradox, black holes will remain one of the biggest mysteries in physics, hiding their secrets behind an event horizon we still don't fully understand. The symmetry-breaking paradox. Symmetry is everywhere in nature. Snowflakes, butterfly wings, even the laws of physics seem to follow patterns that mirror themselves. But sometimes symmetry breaks, and when it does, strange things happen. Imagine a perfectly round ball balanced on the tip of a cone. In theory, it should stay there forever. Every direction is equally valid, so there's no reason for it to fall one way or the other. But in reality, the slightest disturbance, an atom shifting, a gust of air, makes it choose a direction. The symmetry is broken and the ball falls. This is the symmetry-breaking paradox. In physics, the laws governing particles often appear symmetrical, but the universe itself isn't. Take the weak nuclear force, for example. The equations that describe it seem perfectly balanced, yet nature consistently favors one outcome over another. Why? No one knows. Even the Big Bang might be an example of this paradox. The laws of physics suggest equal amounts of matter and antimatter should have been created, canceling each other out. But for some reason, there was slightly more matter, leading to everything we see today. Symmetry breaking is essential for the universe to exist, but it raises a deep question. If the rules are symmetrical, why does reality seem to prefer one outcome over another? It suggests hidden forces at play, tipping the scales in ways we don't yet understand. The anthropic shadow paradox. Some dangers in the universe seem strangely absent. We know that asteroid impacts, supervolcanoes, and even gamma-ray bursts could wipe out life on Earth. Yet here we are. Is it just luck, or is something deeper at play? The Anthropic shadow paradox suggests that we might be missing evidence of catastrophic events simply because we wouldn't be here to observe them if they had happened. Imagine a world where asteroid impacts were far more common, wiping out intelligent life before it ever had a chance to evolve. No one in that world would be around to study asteroid impacts. From their perspective, if anyone existed to have one, asteroids might seem harmless, simply because all the civilizations that encountered them were erased. This is the paradox. We might think world-ending disasters are rare, but what if they're just self-filtering? It's a disturbing idea. The very fact that we are here to ask these questions might mean we've already avoided countless existential threats without realizing it, but it also implies a warning. Just because a disaster hasn't happened in recorded history doesn't mean it won't. There could be extinction-level events we have yet to encounter, events so severe that civilizations before us never had a chance to warn us. The no-cloning theorem paradox. Imagine a machine that could copy anything perfectly, even a living person. Every atom, every thought, every memory, duplicated exactly. It sounds like science fiction, but in the quantum world, something prevents this from happening. The no-cloning theorem states that it is impossible to create an exact copy of an unknown quantum state. In other words, perfect cloning at the quantum level is fundamentally forbidden. Why? Quantum particles exist in superpositions, simultaneously being in multiple states until they are measured. But measurement collapses this superposition into a single outcome. If you tried to copy a quantum state without measuring it, you wouldn't know exactly what to copy. And if you did measure it, the act of measurement would destroy the original superposition. Either way, a perfect copy cannot be made. This paradox challenges many sci-fi ideas, like teleportation and digital consciousness. If perfect quantum copying is impossible, then concepts like beaming a person across space by copying their quantum information might never work. Even attempts at creating backup versions of a mind would fail at the most fundamental level. It raises deep questions about identity. If you can't perfectly clone a person's quantum state, does that mean each conscious being is truly unique? If you were ever copied, would the duplicate really be you, or just an imitation missing something only the original had? The double-slit observer paradox. Light is both a particle and a wave. That's what the famous double-slit experiment shows. When light passes through two slits, it creates an interference pattern, like waves overlapping in water. But here's where things get strange. If you try to observe which slit the light goes through, the interference pattern disappears. Instead, light acts like individual particles, hitting the screen in two distinct bands. Why does simply observing the light change its behavior? This is the heart of the double-slit observer paradox. The act of measurement forces the light to choose between being a wave or a particle. But how does it know it's being watched? The mere presence of an observer alters reality itself. Some physicists believe this hints at a deeper truth about consciousness and the nature of reality. Does observation create reality? If so, what happens when no one is looking? Some interpretations suggest that reality exists in a superposition of possibilities until something or someone collapses it into one definite outcome. This paradox isn't just about light. It challenges everything we think we know about the universe. Are we passive observers, or do we play a fundamental role in shaping what is real? If observation changes reality, then in some sense, reality itself might depend on us. The information loss paradox. Imagine throwing a book into a black hole. The book had words, knowledge, and information, but once it crosses the event horizon, it's gone forever. Or is it? This is where the information loss paradox begins. According to general relativity, anything that falls into a black hole is lost beyond the event horizon. No signal, no data, nothing can escape. But quantum mechanics tells a different story. It states that information can never truly be destroyed. Even if the book is torn apart, its information should still exist somewhere, encoded in the universe. Hawking radiation complicates things. Black holes slowly evaporate over time, leaking energy back into space. But when a black hole disappears, what happens to the information inside? If it's truly lost, it violates a fundamental law of physics, the conservation of information. If it's not lost, then where does it go? Some theories suggest that the information is encoded in the Hawking radiation itself, hidden in subtle quantum correlations. Others propose that it's stored on the event horizon, like a cosmic hologram, or perhaps perhaps the information isn't lost at all, but instead reappears in a parallel universe. The paradox remains unsolved, and at its core lies a bigger question. Does the universe obey strict, unbreakable laws, or is there a deeper, hidden mechanism that we have yet to understand? If information can be lost forever, it may mean our entire understanding of physics is incomplete. The uncertainty principle paradox. Imagine trying to measure the exact position of a tiny particle. The closer you look, the more it moves. So you try to measure its speed instead, but now its position becomes uncertain. No matter what you do, you can't know both at the same time. This is the heart of the uncertainty principle. Werner Heisenberg discovered that at the quantum level, particles don't behave like tiny billiard balls. Instead, they exist in a blur of probabilities. The more precisely you measure a particle's position, the less you know about its momentum, and vice versa. It's not a flaw in our instruments. It's a fundamental limit of nature itself. This leads to a strange paradox. If you can't know both a particle's position and momentum exactly, then reality itself is uncertain. The act of observing something changes what you're observing. In other words, the world doesn't have definite properties until it is measured. This principle challenges our classical view of reality. How can something exist in multiple states until it is observed? Does this mean reality is not fixed until we look at it? Some interpretations suggest that particles exist in all possible states at once, only collapsing into a definite form when observed. But if observation changes reality, what does that say about the universe? Is it only real because we're looking at it? If no one observes a quantum event, does it even happen? The uncertainty principle forces us to question whether reality is something objective or something shaped by our own perception. The delayed choice, quantum eraser paradox. Imagine firing a single particle, like a photon, toward a barrier with two slits. If you don't measure which slit it goes through, it behaves like a wave, interfering with itself and forming a pattern. But if you place a detector to see which slit it passes through, the interference disappears, and it behaves like a particle instead. Now, here's where things get stranger. In the delayed choice quantum eraser experiment, the decision to measure the particle is made after it has already passed through the slits. Yet somehow, this choice still affects its past behavior. It's as if the particle knows whether it will be observed, even retroactively adjusting its history. How can a future decision determine a past event? Did the particle go through one slit or both? The paradox suggests that reality is not fixed until information is observed, even if that observation happens later in time. It challenges our common sense idea that the past is set in stone. Some interpretations say this hints at a universe where information, not just physical objects, is the foundation of reality. Others suggest that time itself may not be as linear as we assume. Could reality be determined not just by the past leading to the future, but by future choices shaping the past? If so, what does that say about free will? And is the universe truly deterministic, or is it shaped by our choices in ways we can't yet understand? The Planck scale reality paradox. At the scale of everyday life, reality seems smooth and continuous, but as you zoom in to the level of atoms, then subatomic particles, things start behaving strangely. And if you go even further, down to the Planck scale, the smallest possible scale in physics, something bizarre happens. The Planck length, about 1.6 times 10 to the power of negative 35 meters, is the point where our understanding of space and time breaks down. Below this, quantum mechanics and general relativity stop making sense together. Space itself may no longer be continuous, but instead exist in discrete pixel-like chunks. Reality, as we know it, might not be infinitely divisible. It could be made of fundamental indivisible units, like the pixels on a screen. But this leads to a paradox. If space is not continuous, what happens to movement? Can anything actually travel through a universe made of discrete chunks? If motion is just hopping from one point to another, what determines the jumps? And if time also becomes quantized at this scale, does it mean the universe operates more like a digital simulation than a smooth, flowing reality? Some theories suggest that below the Planck scale, space-time itself dissolves into a foam-like state where traditional physics no longer applies. Others propose that our entire concept of space is just an emergent property of something deeper, something we can't yet grasp. But if reality is built from indivisible units, does that mean we're living inside a programmed universe? Or is it simply that our theories are incomplete and reality is stranger than we ever imagined? The vacuum catastrophe paradox. Imagine trying to calculate the energy of empty space. In quantum mechanics, even a vacuum isn't truly empty. Instead, it's a seething ocean of virtual particles popping in and out of existence. The equations predict that this vacuum energy should be enormous, so large that it should rip the universe apart. Yet when physicists measure the actual energy of space, it's nearly zero. The predicted and observed values don't just slightly disagree, they differ by a factor of 10 to the power of 120. That's a number so large it defies comprehension, the biggest mismatch in physics. If the vacuum had as much energy as predicted, gravity would amplify it, accelerating the universe's expansion at an unimaginable rate. Galaxies, stars, and even atoms would be torn apart instantly. But the universe exists. Matter is stable. Something is wrong with our understanding. The vacuum catastrophe highlights a deep contradiction between quantum mechanics and general relativity. One possibility is that there's an unknown mechanism canceling out most of this energy. Another is that our theories are incomplete, missing a fundamental piece of reality. Some suspect the answer lies in a future theory of quantum gravity, something beyond our current physics. Until then, the vacuum catastrophe remains one of the greatest unsolved mysteries, a paradox hiding at the very foundation of existence. The consciousness field paradox. Imagine if consciousness wasn't just a byproduct of the brain, but a fundamental field, like gravity or electromagnetism. Some theories suggest that awareness isn't created by neurons. It's something the brain taps into, like a radio picking up signals. This raises a strange question. If consciousness exists independently, then why does brain damage or anesthesia alter it? Shouldn't it remain unaffected, like a signal that keeps broadcasting regardless of the receiver? This paradox challenges how we define awareness. If consciousness is a fundamental part of reality, it should persist even when the brain is impaired. But every medical case suggests otherwise. Patients with brain injuries often lose memories, personality traits, or even self-awareness. It's as if consciousness isn't an external field, but something produced within the brain itself. Yet some near-death experiences and quantum theories hint that awareness might not be confined to biology. If consciousness is fundamental, why does it rely on the brain's structure? And if it's purely a product of biology, why do some claim to experience it beyond death? The paradox leaves us in an uncertain place. Are we individual minds shaped by our neurons, or are we all just receivers, tuned into something greater? The split brain perception paradox. Imagine a person with a severed corpus callosum, the bridge connecting the brain's left and right hemispheres. This is sometimes done to treat severe epilepsy, but it reveals something unsettling. When the two halves of the brain can't communicate, they start acting like separate minds. One side may recognize an object, but the other side won't be able to name it. A patient might pick up a spoon with their left hand, but insist they don't see anything when asked. This raises a bizarre question. If the brain is split, is consciousness split too? Is there now more than one person inside the same body? Normally, we assume a single unified self, but these cases suggest otherwise. Each hemisphere seems to have its own awareness, responding differently to stimuli. One side can even make choices without the other knowing. If the two halves function independently, what happens to the original you? The paradox forces us to rethink identity. If consciousness is divided, does that mean it was never a single thing to begin with? Are we just an illusion created by a working brain, a collection of separate processes pretending to be whole, or is there something deeper that ties it all together, something beyond the physical connections? The answers challenge what it means to be a self at all. The Boltzmann brain paradox. Imagine the universe stretching for eternity, filled with endless randomness. Over vast timescales, atoms randomly collide, forming stars, planets, and even life. But there's a strange idea buried in this chaos. What if your brain, with all its memories and thoughts, just randomly formed out of nothing, not as part of a body, not as part of a civilization, but as a single, floating brain in the void, momentarily conscious, before dissolving back into randomness? This is the Boltzmann brain paradox. The idea comes from physics and probability. If the universe is infinite and chaotic, then it's actually more likely that a self-aware brain would randomly appear than an entire structured world like ours. A full universe requires precise conditions, laws of physics, complex systems, billions of years of evolution, but a single brain, briefly forming with fake memories of a life it never lived. That's statistically far easier. So how do you know you're not a Boltzmann brain? How do you know your memories are real and not just the result of a random fluctuation? The paradox suggests that in an infinite timeline, consciousness Conscious minds like ours should be far rarer than isolated, fleeting Boltzmann brains. And yet, we experience a stable reality filled with patterns, history, and continuity. Does this mean our universe isn't infinite, or is there something deeper anchoring our sense of self? The paradox remains one of the strangest thought experiments in cosmology. The retrocausality paradox. Cause and effect. One thing leads to another. You wake up because your alarm rings. You eat because you're hungry. But what if effect could come before cause? What if the future could change the past? This is the strange idea behind retrocausality, the possibility that events in the future can influence or even determine what happens in the past. It sounds impossible, but quantum mechanics suggests otherwise. In experiments, particles seem to change their behavior based on choices made later in time. The delayed choice quantum eraser experiment, for example, shows that a particle's past state can be determined by a decision made in the future. If reality works like this, then cause and effect are not as straightforward as they seem. The paradox arises when we apply this to everyday life. Imagine you receive a message from your future self warning you about a mistake. You change your actions, avoiding the mistake entirely. But if the mistake never happened, why would your future self have sent the message? If the warning causes the event to never occur, then the reason for sending it disappears, creating a contradiction. Retrocausality challenges our understanding of time itself. If the future can affect the past, does free will still exist? Are we simply following a predetermined path where future choices have already shaped the present? If time isn't linear, then the very concept of cause and effect may be an illusion, and reality might be far stranger than we ever imagined. The holographic universe paradox. Reality feels three-dimensional. You can move forward, backward, up, down. Everything has depth. But what if this is an illusion? What if the entire universe is nothing more than a projection, like a hologram? This is the strange idea behind the holographic universe paradox, a concept that challenges everything we think we know about space, time, and reality itself. The paradox starts with black holes. Physicist Stephen Hawking discovered that black holes slowly evaporate, but this led to a problem. If information falls into a black hole and disappears, that would break the fundamental laws of physics. Information, according to quantum mechanics, should never be lost. But then a strange solution appeared. What if information isn't stored inside a black hole, but on its surface, like a two-dimensional imprint? This idea led to something even bigger. Some physicists believe that the entire universe might work the same way. What we see as three-dimensional space could be a projection from a two-dimensional surface at the edge of the universe. If this is true, then everything, planets, galaxies, even your own consciousness, might just be a holographic representation of deeper, hidden information. But if reality is a projection, what does that mean for our existence? Are we real, or are we just data encoded on a cosmic boundary? Does this mean free will is an illusion, determined by an underlying code we can't perceive? If the universe itself is a hologram, then what lies beyond the projection? And if everything we experience is just a surface-level representation of something deeper, then what is truly real? The false vacuum paradox. The universe seems stable, stars burn, planets orbit, and the laws of physics remain the same. But what if this stability is an illusion? What if the universe is just in a temporary state of balance, one that could collapse at any moment? This is the terrifying possibility of the false vacuum paradox, a scenario where reality itself could be erased in an instant. The idea comes from quantum field theory. The universe is thought to exist in a state of lowest possible energy, called the true vacuum. But what if it doesn't? What if the universe is stuck in a false vacuum, a local energy minimum that only seems stable? If so, then a tiny fluctuation, maybe triggered by quantum tunneling or even a high-energy event, could push the universe into a lower energy state, the true vacuum. And if that happens, everything changes. This transition wouldn't be slow. It would expand outward at the speed of light, erasing everything in its path. Atoms, stars, even the fundamental forces could be rewritten in an instant. And the worst part? We wouldn't see it coming. There would be no warning, no way to prepare. One moment, reality as we know it exists. The next, it's gone, replaced by a new set of physics that may not even allow life to exist. But if the universe is truly in a false vacuum, why hasn't this collapse happened yet? Is there something protecting us, or are we just incredibly lucky? And if reality can vanish without a trace, does anything we do really matter? Or are we all just living on borrowed time, waiting for an event that could erase existence itself? The entropic gravity paradox. Gravity feels like one of the most fundamental forces in the universe. It holds planets in orbit, pulls objects toward the ground, and keeps galaxies together. But what if gravity isn't actually a force at all? What if it's just an illusion, a side effect of something even deeper? This is the strange idea behind the entropic gravity paradox, proposed by physicist Eric Verlinde. It suggests that gravity isn't a fundamental interaction like electromagnetism or the nuclear forces. Instead, it emerges from entropy, the natural tendency of systems to increase in disorder. In this view, space itself is like a vast, complex information system. When matter moves, it disturbs the system, changing how information is arranged. The result? A force that behaves just like gravity, but isn't actually pulling anything. It's just a byproduct of information reshuffling itself. If true, this changes everything. Black holes, for instance, may not be objects with an actual gravitational pull, but information hubs where entropy reaches its maximum limit. Dark matter, the invisible substance thought to make up most of the universe's mass, might not even exist. Its effects could simply be the result of misunderstood entropic processes. And if gravity is just information responding to changes, then what does that say about reality itself? Does this mean gravity is nothing more than a trick of the universe? If space and time are just emergent properties of deeper laws, then how much of what we perceive is real? And if the very force that binds the cosmos is just a statistical effect, what other fundamental truths might turn out to be illusions? The gravitational time dilation paradox. Time feels constant. Seconds tick by, minutes pass, and hours turn into days. But what if time doesn't flow the same for everyone? What if your watch, right now, is moving at a completely different speed than someone else's, just because of where you are? This is the mystery of gravitational time dilation. According to Einstein's theory of relativity, time moves slower in stronger gravitational fields. The closer you are to a massive object, like a planet or a black hole, the slower time passes for you compared to someone farther away. It sounds like science fiction, but it's been proven satellites orbiting Earth experience time slightly faster than we do on the surface, so their clocks must be constantly adjusted to keep GPS systems accurate. Astronauts on the International Space Station age just a tiny bit slower than people on Earth. But here's where the paradox begins. Imagine two twins. One stays on Earth while the other travels near a black hole, where gravity is extreme. Time feels constant. Seconds tick by, minutes pass, and hours turn into days. But what if time doesn't flow the same for everyone? What if your watch, right now, is moving at a completely different speed than someone else's, just because of where you are? This is the mystery of gravitational time dilation. According to Einstein's theory of relativity, time moves slower in stronger gravitational fields. The closer you are to a massive object, like a planet or a black hole, the slower time passes for you compared to someone farther away. The missing baryon paradox. Everything you see, touch, and experience is made of baryonic matter, the protons and neutrons forming atoms, planets, and stars. But what if half of this matter was simply missing? For decades, physicists have faced a troubling mystery. When they calculate how much baryonic matter should exist in the universe based on the Big Bang and cosmic background radiation, there's a problem. Roughly half of it is nowhere to be found. It's not in galaxies, not in interstellar space, and not hidden inside black holes. It's just missing. This isn't dark matter, the invisible mass that makes up most of the universe's gravity. No, this is regular, everyday matter, the same kind that makes up you, me, and everything around us. So where did it go? Scientists have searched in the vast cosmic web, the filaments of gas connecting galaxies, and even in the scorching heat of intergalactic space. Some believe these missing baryons are trapped in the invisible plasma between galaxies, too spread out to be detected. Others think they exist in faint, undetectable clouds drifting through the universe. But here's the paradox. If we can't find this missing matter, does it even exist? How can we be sure the universe follows the rules we think it does? If half of normal matter is unaccounted for, then how much do we really understand about the universe? And if something as basic as matter itself can disappear without explanation, what else might be hiding beyond our reach? The quantum unaliving paradox. Imagine a weapon that is connected to a quantum particle. Every time you pull the trigger, the particle is measured. If it spins one way, the weapon fires. If it spins the other way, it doesn't. The key is that quantum mechanics says the particle exists in both states at once until it's observed. Now suppose you sit in front of this weapon and pull the trigger. According to the Copenhagen interpretation of quantum mechanics, the particle collapses into one state or the other. You either live or die, chosen at random. But the many worlds interpretation says something different. It says that both outcomes happen, just in different universes. In one universe, you die. In another, you survive. Here's where things get strange. If you keep pulling the trigger, in some universes, you die early. But in at least one universe, the weapon never fires. The particle just keeps landing in the safe state every time. From your perspective, you are immortal. No matter how many times you try, you always find yourself in the reality where you survive. But here's the paradox. If this is true, then why aren't we surrounded by people who have lived forever? Why hasn't someone tested this theory and become unkillable? Maybe they have, just not in our universe. Or maybe consciousness itself doesn't work the way we think. If survival is guaranteed in some realities, then what does that say about fate, probability, and the true nature of existence? The eternal inflation paradox. The universe is expanding, not just slowly drifting apart, but accelerating outward, driven by an invisible force called inflation. This idea explains why the cosmos looks so uniform, why galaxies are spread out the way they are. But inflation doesn't just stop, it keeps going, endlessly creating new regions of space. And this is where the paradox begins. In most versions of inflation theory, while our observable universe settled into a stable state after the Big Bang, inflation continued elsewhere. It never fully ends everywhere at once. Instead, it keeps bubbling outward, creating an infinite number of new universes forever. This process, called eternal inflation, suggests that new universes are constantly being born. But if inflation is eternal, and if an infinite number of universes are being created, then every possible version of reality must exist somewhere. There must be a universe where you never existed, another where you never stopped existing, a world where history played out exactly as you remember, except for one tiny detail. Here's the paradox. If eternal inflation means infinite possibilities, why does our universe seem so predictable? Why do we experience time moving in one direction instead of jumping between different realities? If new universes are forming infinitely, then doesn't that mean somewhere, someone identical to you is having this exact thought right now? Maybe even infinitely many versions of you. And if that's true, then what does you even mean? The expanding universe paradox. The universe is getting bigger. Every second, galaxies drift farther apart, space itself stretching like an inflating balloon. Scientists have measured this expansion, and it's not slowing down, it's accelerating. The further away a galaxy is, the faster it moves. This leads to a strange paradox. If the universe is expanding, what is it expanding into? When we imagine something growing, we picture it inside something larger. A balloon expands into the air around it. A ripple in water spreads across the surface. But space itself is growing. There's no outside, no edge. The universe isn't expanding into anything. It's just expanding. But how can something grow without having boundaries? It gets weirder. If the universe has no edge, then where's the center? If everything is moving away from everything else, then every point in space is equally the center. But that doesn't make sense. How can something be expanding if it has no central point, no fixed location to measure from? And here's another twist. If space is expanding, why don't we feel it? Shouldn't the space between atoms, between you and everything else, be stretching too? Yet your body stays the same size. The Earth doesn't expand. Even our solar system remains unchanged. Only the vast distances between galaxies grow. The paradox challenges our understanding of space itself. The universe expands, but not into anything. It has no center, yet everything moves away. And while galaxies drift apart, the space around us feels completely still. So, is expansion real, or is our perspective what's truly shifting? The dimensional awareness paradox. Imagine a world that exists in only 2 dimensions, like a drawing on a piece of paper. The beings in this world, let's call them flatlanders, can move left, right, forward, and backward. But they have no concept of up or down. To them, a third dimension is impossible to perceive. Now, what if we are just like the Flatlanders, limited by our own three-dimensional reality? We move through space effortlessly, but time is different. We can't revisit the past or skip ahead to the future at will. Yet physicists describe time as the fourth dimension. If that's true, why can't we see it? If higher dimensions exist beyond our perception, what else are we blind to? Here's the paradox. If we were truly limited to our dimensions, we wouldn't even be able to imagine higher ones. But we do. We can conceptualize a fourth, a fifth, even an 11th dimension in mathematical models. We can describe them, calculate them, but never physically experience them. It's like a Flatlander trying to understand a cube. Impossible from their perspective, but obvious to us. If higher dimensions exist all around us, then why don't we see any evidence of them? Or what if we do, but we simply don't recognize it? Could our inability to perceive them be the very thing keeping us unaware? If an entire reality exists beyond our senses, how would we ever know? The relativity of simultaneity paradox. Imagine two people watching the same event from different places. A lightning bolt strikes at both ends of a moving train. To an observer standing on the platform, the strikes appear to happen at the same time. But to someone inside the moving train, something strange happens. Because the train is moving forward, the light from the front strike has to travel a longer distance to reach the passenger, while the light from the back strike travels a shorter distance. Even though both flashes moved at the speed of light, the one from the back reaches the passenger first. To them, the two strikes did not happen at the same time. Here's the paradox. If two people can disagree on whether events happened simultaneously, then what does "at the same time" really mean? If simultaneity is not absolute, then time itself is not absolute. Two different realities exist at once. Both observers are correct in their own frames of reference. This isn't just a thought experiment. Einstein's theory of relativity proves that time and space shift depending on how fast you move. If someone were traveling close to the speed of light, their version of time could be completely different from yours. Does this mean there's no objective now? If time is just a perspective, then what happens to the idea of a single, shared reality? The Turing-Halting paradox. Imagine a machine that can analyze any program and determine whether it will eventually stop or run forever. Let's call this machine the halting oracle. It takes in a program and its input, then confidently declares either halts or runs forever. Now let's push this idea further. What if we create a strange program that does the opposite of what the halting oracle predicts? If the oracle says the program will halt, the program enters an infinite loop. If the oracle says it will run forever, the program immediately stops. What happens when we feed this paradoxical program into the oracle? If the oracle predicts it will halt, the program contradicts it by running forever. But if the oracle predicts it will run forever, the program contradicts it by halting. The oracle is now trapped in an unsolvable contradiction. It cannot make a correct prediction. This paradox, discovered by Alan Turing, proves a shocking truth. There is no perfect way to determine whether any given program will halt. Some problems are simply undecidable. If no machine can universally solve this problem, does this mean there are limits to computation itself? And if certain questions can never be answered, what does that say about the nature of knowledge? The brain-in-a-vat paradox. What if everything you see, hear, and feel is a lie? Imagine that instead of living in the real world, your brain is floating in a vat connected to a supercomputer. This machine sends electrical signals to your neurons, perfectly simulating reality. Your experiences, walking through a park, feeling the sun, tasting your favorite food, are nothing more than artificial impulses. How would you ever know? This thought experiment challenges the very foundation of knowledge. If all your senses can be manipulated, then how can you be sure that anything you perceive is real? You might argue that your experiences feel consistent, but that could just be part of the simulation. Even your thoughts questioning reality could be programmed responses. Philosophers have wrestled with this idea for centuries. Descartes famously questioned whether an evil demon could be deceiving him, while modern versions replace the demon with advanced technology. The paradox forces us to consider, if we can't prove we aren't brains in vats, then can we ever truly know what's real? And if we can't, does reality even matter? The unsolvable problem paradox. Imagine you're given a puzzle, a challenge so complex that no matter how much time you spend, no matter how intelligent you are, you will never find a solution. At first, this seems impossible. Every problem must have an answer, right? But what if some problems are fundamentally unsolvable? Mathematician Kurt Gödel introduced this idea with his incompleteness theorems, proving that in any formal system of logic, there will always be true statements that can never be proven. In other words, there are limits to what we can ever truly know. Some questions will forever remain unanswered, not because we aren't smart enough, but because they cannot be solved within the system we use to understand reality. This paradox challenges our deepest assumptions. If an unsolvable problem exists, how can we ever be sure that anything we believe is complete? What if the ultimate truths of the universe are beyond our reach? If no solution exists, is searching for one meaningless, or does the pursuit itself have value? The infinity loop paradox. Imagine a staircase that never ends. You walk up step after step, believing you're getting higher, yet somehow you find yourself right back where you started. No exit, no conclusion, just an endless cycle. This is the essence of the infinity loop paradox, where a sequence repeats forever without resolution. In mathematics, infinity is often treated like a number, but it's not. It's a concept, one that defies logic. Consider a hotel with infinite rooms, all occupied. A new guest arrives, and the manager simply shifts every guest one room over, making space where none existed. This is Hilbert's paradox of the Grand Hotel, a demonstration that infinity follows rules unlike anything in our everyday world. But infinity loops aren't just mathematical curiosities. In physics, time could be infinite, leading to endless repetitions of history. In philosophy, the idea of eternal recurrence suggests that our lives may be relived an infinite number of times. If true, are we trapped in a loop, making the same choices forever? And if a cycle has no starting point, can we ever find a way out? Or are we doomed to chase answers that never arrive? The Laplace's demon paradox. Imagine a being that knows the position and velocity of every particle in the universe, a mind so powerful that given the laws of physics, it could calculate the entire past and predict the entire future with perfect accuracy. No surprises, no randomness, just pure determinism. This is Laplace's demon, a thought experiment that raises one of the deepest questions in science and philosophy. Is free will just an illusion? If everything in the universe follows physical laws, then in theory, the future is already written. Every thought you have, every choice you make is just a chain reaction from the past. But here's the paradox. Quantum mechanics suggests the universe isn't predictable at all. Particles don't follow strict paths. They exist in probabilities. If true, Laplace's demon would fail before it even begins. But even if the universe is deterministic, another question emerges. If everything is set in stone, then so is the demon itself. It would be trapped, unable to change its own mind. Could it truly have knowledge of the future if it's also part of the system? Or would its own existence create an infinite loop, forever preventing it from achieving the very thing it was designed to do? The Fermi paradox. The universe is vast, trillions of stars, countless planets, billions of years of existence. If life on Earth emerged relatively quickly, shouldn't intelligent life be everywhere? And yet, when we look up at the stars, we see nothing. No signals, no visitors, no evidence. This is the Fermi paradox, the unsettling contradiction between the high probability of extraterrestrial civilizations and the complete lack of contact with them. There are many possible explanations. Maybe advanced civilizations self-destruct before they reach interstellar travel. Nuclear war, environmental collapse, artificial intelligence, any of these could wipe out a species before they expand into the cosmos. Or perhaps they're here, watching, but unwilling to interfere. Maybe intelligent life tends to stay silent, fearing a universe that could be hostile. Another possibility is that we're alone, or at least one of the first. Life may be far rarer than we think. Perhaps it requires an incredibly specific set of conditions, so unique that it almost never happens. Or maybe the universe is teeming with civilizations, but the vast distances make communication nearly impossible. If life is common, where is everyone? If it's rare, how did we get so lucky? The answer could change everything we know about our place in the cosmos. The Alcubierre bubble paradox. Faster than light travel is impossible, at least according to everything we know about physics. But the Alcubierre drive suggests a loophole. Instead of moving an object faster than light, It bends space itself, compressing space in front of a ship and expanding it behind, creating a warp bubble that carries the ship forward. In theory, this allows for faster than light travel without violating the laws of physics. But this idea comes with a paradox. If a ship inside the bubble isn't moving relative to its own space, how does it control where it goes? Normal movement relies on forces acting within space, but in a warp bubble, the ship is locked in, unable to interact with the space outside. Once the bubble forms, it becomes a self-contained pocket, cut off from the rest of the universe. That means the ship inside wouldn't be able to steer, slow down, or stop. The bubble would travel until it naturally dissipates, wherever that may be. There's also the problem of energy. The Alcubierre drive requires negative energy, a theoretical form of exotic matter that may not even exist. And if it does, it might be impossible to control. Even if we found a way to generate and manipulate it, the amount required would likely exceed anything we could ever produce. A drive that bends space itself sounds like the ultimate breakthrough, but if we can't control it, can't stop it, and can't power it, is it really a path to the stars, or just a beautiful, impossible dream? The perception-reality paradox. What if everything you know about reality is just an illusion? Your senses tell you the world is solid, colorful, and full of sounds, but physics suggests otherwise. The colors you see don't exist, only different wavelengths of light. The sounds you hear are just vibrations in the air. Even the feeling of solidity is an illusion, since atoms are mostly empty space. Your brain doesn't show you the world as it is. It shows you the world as it needs to be for you to survive. This raises a paradox. If our perception of reality is just a filtered version of the truth, then what is reality really like? We assume we experience the world accurately, but our senses are limited. We can't see infrared light like snakes do. We can't hear the ultrasonic frequencies bats use to navigate. We can't sense the magnetic fields that guide birds. If these invisible forces shape the universe, how much of reality are we truly missing? Even time itself might not be what we think. We experience time as a flowing river, moving from past to future, but physics suggests all moments exist at once, like a frozen block. Is time moving, or is our mind just making it feel that way? If perception isn't reality, then how can we ever know what reality truly is? Is truth something we can grasp, or are we forever trapped inside the limits of our own mind, mistaking the shadows on the wall for the world beyond? The grandfather time loop paradox. Imagine you invent a time machine. You travel back in time, decades before you were born. As you explore the past, a troubling thought crosses your mind. What would happen if you prevented your own grandfather from ever meeting your grandmother? If they never meet, your parent is never born. And if your parent is never born, neither are you. But if you were never born, how did you go back in time in the first place? This is the classic grandfather paradox. But now, add a twist, a loop with no beginning. Instead of preventing your birth, imagine you go back in time and accidentally cause your grandparents to meet. Without your interference, they might never have fallen in love. So your journey to the past is the very thing that ensures your own existence. This creates a closed time loop. Your life depends on an event that was only triggered by your own actions in the past. But if your involvement caused that event, then where did the original event come from? Did it ever have a true starting point, or is it caught in an endless cycle repeating itself forever? The paradox suggests that time might be self-contained, with no need for an initial cause. If the loop has no beginning, then what does that say about time itself? Could the entire universe be trapped in a repeating cycle where every effect is also its own cause? And if reality is just an infinite loop, then is the past truly set in stone, or is the future shaping it as much as it shapes the future? The dark flow paradox. The universe is expanding in every direction, driven by a mysterious force we call dark energy. But in one region of the cosmos, something strange is happening. Galaxies are not just moving with the general expansion of the universe. They're drifting in one specific direction, as if being pulled by an unseen force. Scientists call this unexplained motion dark flow. The problem? According to our best models of cosmology, this shouldn't be happening. The cosmic microwave background, the afterglow of the Big Bang, suggests that the universe should be uniform on large scales. Gravity from known structures, like galaxies and clusters, isn't strong enough to explain this motion, and yet entire clusters of galaxies, billions of light years away, seem to be heading toward a mysterious unknown point beyond the observable universe. Some scientists suggest that dark flow could be the result of massive structures lying outside our cosmic horizon, perhaps remnants of a universe that existed before the Big Bang. Others speculate that it could be the evidence of a parallel universe, one that is exerting a gravitational pull on our own. But if that's the case, then what does that mean for the nature of reality? Are we part of a much larger cosmic system, one we can never fully see or understand? If dark flow is real, it challenges everything we know about the structure of the cosmos. It suggests that our universe might not be the only one, and that the forces shaping our reality could extend far beyond anything we can observe. But if we can never see what's causing it, then is the universe truly infinite, or is it simply part of something even greater? The simulation boundaries paradox. If reality is a simulation, then where does it end? In a video game, you eventually reach the edge of the map, the point where the world stops rendering. But if we are living in a simulated universe, is there a boundary we could find? A place where the illusion breaks down? Some physicists believe that the fundamental limits of our universe, like the speed of light or the Planck length, could be signs of these boundaries. In a computer simulation, there are limits to resolution. Pixels define how detailed an image can be. What if the universe operates the same way? If space and time are not continuous, but instead made up of the smallest possible units, then maybe we are just looking at the rendering quality of our simulation. Quantum mechanics itself hints at something strange. The observer effect shows that reality doesn't fully exist until it is measured. Like a video game that only loads the environment. When a player looks in a certain direction, maybe the universe only renders details when they are needed. But what happens if we push beyond its limits? If we build better technology, observe reality at an even deeper level, will we eventually see the edges of the simulation, or is the paradox deeper? If we ever did find the boundary, would that prove we're in a simulation, or would it just mean our understanding of physics is flawed? If reality is coded, then who or what is running the simulation? And if we reach the limits, do we risk breaking the very fabric of our existence? The Mandelbrot infinity paradox. Imagine zooming into a picture, expecting to reach the smallest detail, but instead you find more details, shapes within shapes, repeating endlessly. No matter how deep you go, the complexity never ends. This is the paradox of the Mandelbrot set, a mathematical object that defies our intuition about space, scale, and infinity. At first glance, the Mandelbrot set looks like an ordinary fractal pattern, but when you zoom in, the same patterns reappear, infinitely nested within themselves. It's not just repetition, it's infinite complexity emerging from a simple equation. No matter how far you magnify it, there's always more to see. In theory, you could zoom in forever without ever reaching a final, smallest piece. This raises a paradoxical question. If something contains an infinite amount of detail within a finite space, does it truly have a limit? Normally, when we think about infinity, we imagine something stretching endlessly outward. But here, infinity is trapped within a boundary. It suggests that even within something small, there might be infinite layers of complexity, hidden dimensions, endless recursion, an unbreakable cycle of detail. What if the universe itself works this way? If space, time, and matter are structured like a fractal, then reality may have no fundamental building block. There could always be another layer beneath, a deeper structure beyond our current understanding. And if that's true, then the search for the smallest particle, the most fundamental law, might never end. But the real paradox is this: if infinity can fit within a finite space, does that mean we are also trapped within one? If everything we perceive is just another level of recursion, then how can we ever be sure that what we see is the true foundation of reality? Or are we just zooming in on yet another layer forever? The Schrodinger's dream paradox. You wake up in the morning, stretch, and begin your day. But then a strange thought enters your mind. What if you're still dreaming? How do you know this moment is real? You pinch yourself. It hurts. That means you're awake, right? But then, what if the pain itself is part of the dream? This is the paradox of Schrodinger's dream, a reality caught between states, where you are both dreaming and awake until proven otherwise. It's inspired by Schrodinger's famous thought experiment, where a cat in a box is both alive and dead until observed. In a similar way, your experience is in a superposition of real and dream until something confirms one state over the other. But here's the problem. What counts as confirmation? If everything within a dream can feel real, then how do you ever know when you've truly left it? Lucid dreamers describe moments where they thought they had woken up, only to realize they were still trapped in another layer of the dream. Some report waking up multiple times, each moment feeling just as real as the last. So if the experience of reality can be simulated perfectly within your own mind, what makes waking life any different? What if you're only in another layer now, one that just feels more convincing? missing. This paradox raises a disturbing possibility. If you can never be fully certain when you're dreaming, then is it possible that you've never actually woken up at all? What if consciousness itself is just an endless series of nested dreams, where every awakening is just another illusion? And if that's true, then how do you escape? Or worse, what if there is no escape? The mind upload paradox. Imagine a future where technology has advanced to the point where you can upload your mind to a computer. Every thought, memory, and personality trait copied with perfect precision. The moment arrives, and you activate the upload. But as you sit in the chair watching the progress bar fill, a terrifying thought strikes you. When the upload is complete, will you still be you? Or will your consciousness die with your body while the copy believes it's you? This is the mind upload paradox. If your brain is scanned and transferred to a digital system, is that uploaded version really you, or just an incredibly accurate copy? If someone made 2 uploads, which one is you? What if the original you is still alive? Do you exist in 2 places at once, or does one of you become an imposter? Some argue that identity isn't tied to a single physical brain, but to the pattern of information within it. If the copy thinks, feels, and remembers everything just like you, then from its perspective, nothing has changed. But from your perspective, something is missing. You, the one sitting in the chair, still trapped in your biological body. If someone pulled the plug on you right after the upload, would you continue as the digital version, or would that simply be another consciousness that only believes it was once you? The paradox deepens when you consider gradual uploads. What if your brain was slowly replaced, neuron by neuron, with artificial parts until it was entirely digital? At what point do you stop being yourself? Or do you ever? If a perfect copy of you can be made, does that mean you were never truly unique to begin with? And if consciousness can be duplicated, then what does it even mean to be you? The nothingness expansion paradox. Imagine the universe expanding, not just galaxies moving apart, but space itself stretching, growing larger every second. But here's the question: what is it expanding into? If the universe is everything, then what lies beyond its edge? And if nothing is there, can nothing even exist? This is the nothingness expansion paradox. If the universe has a limit, then there must be something outside of it. But if there is something, then that means the universe isn't truly everything. And if the universe is infinite, then why does it need to expand at all? What would it be expanding into? Nothing. But nothing isn't a thing. It's the absence of anything. If something expands into nothing, does the nothing become something? Some scientists say the universe doesn't need to expand into anything. Instead, space itself is stretching, creating more distance between objects without requiring an outside. But that explanation feels unsatisfying. If space is growing, there should be a boundary, an edge where space stops, and something else, perhaps true nothingness, begins. But here's another problem. If there were an edge, you could theoretically reach it. And if you did, what would happen if you stepped beyond? Would you vanish? Would you find another universe? Or would you discover a place where space simply doesn't exist? Then there's the possibility that our understanding of nothingness is flawed. Maybe the universe isn't expanding into nothing because nothing, in the truest sense, can never exist. Perhaps what we call nothing is just something we haven't yet defined. But if nothing has never existed, then what was there before the universe began? Was there ever truly a before? And if space and time didn't exist before the universe, then how did something appear at all? The Wheeler's delayed choice paradox. Imagine you shine a single photon of light at a distant galaxy. On its way, the photon passes a massive gravitational lens, an enormous object that bends light, splitting the photon's possible paths in two. It could go left or right around the object before reaching Earth. You might think the photon makes its choice at the moment it encounters the lens. But what if you only decide to measure its path long after it has passed the lens? This is the Wheeler's delayed choice paradox. It suggests that a photon doesn't truly choose its path until an observer measures it, even if that decision happens long after the photon should have already traveled one path or the other. Before measurement, it remains in a quantum superposition, taking both paths at once. But the moment you decide to observe it, the past seems to change. It's as if reality only settles on a definite history when someone looks. The paradox raises disturbing questions about time and causality. If the act of measurement determines what happened in the past, then does the past truly exist before it's observed? And does Does reality only take form when something interacts with it? And if that's true, how much of the universe remains in a state of uncertainty until we look? Some physicists argue that reality isn't rewritten, but is instead fundamentally probabilistic. The photon doesn't take a definite path until it's forced to reveal one. But that explanation only deepens the mystery. If observation finalizes history, then does the universe depend on conscious observers to exist? And if no one were watching, would anything have ever happened at all? The quantum decoherence paradox. Imagine you are observing a quantum particle, say an electron. In theory, it exists in multiple states at once, a superposition of possibilities. But the moment you measure it, the wave function collapses, and it chooses one definite state. The paradox isn't just that measurement forces a decision, it's that superpositions seem to vanish the instant a system interacts with its surroundings. This is quantum decoherence. The delicate quantum state of the electron doesn't survive contact with the environment. Any interaction, light, air, or even heat, erases its superposition, making it behave like a classical particle. It's as if reality constantly forces choices, preventing quantum weirdness from persisting in the macroscopic world. But here's the paradox. If decoherence explains why we don't see superpositions, does that mean reality only seems classical because of interactions? What if quantum states never actually collapse, but just spread out beyond our ability to measure? Some physicists suggest that different possibilities still exist in separate branches of reality, aligning with the many worlds interpretation. If that's true, then every quantum event splits the universe into countless parallel timelines. So, is quantum collapse real, or is it just an illusion of our limited perspective? If everything follows quantum rules at a fundamental level, then is our everyday reality just one version among infinite unseen possibilities? The observer effect paradox. Imagine a simple experiment. You fire a beam of electrons through two slits in a barrier, aiming at a screen behind it. If you don't measure which slit they pass through, the electrons behave like waves, creating an interference pattern on the screen. But the moment you observe them, the pattern changes. The electrons act like particles, choosing one slit or the other. This is the observer effect. The act of measuring changes the outcome. But why? Does an electron somehow know it's being watched? It seems as if consciousness itself influences reality. This raises an unsettling question. Is reality fundamentally different when unobserved? Some interpretations of quantum mechanics suggest that particles don't have definite properties until measured. Before observation, they exist in a cloud of probabilities, as if waiting for reality to be determined. But what counts as an observer? A human? A camera? A single photon bouncing off the electron? If any interaction is enough to collapse the wave function, then doesn't everything observe everything else all the time? The paradox is this. If observation changes reality, then does reality even exist in a definite state when no one is looking? Or is everything just a blur of probabilities, solidifying only when we pay attention? And if so, what does that mean for the nature of existence itself? The many worlds identity paradox. Imagine you make a simple choice, left or right. In the many worlds interpretation of quantum mechanics, both choices happen. The universe splits, creating two versions of reality. One where you went left, another where you went right. Every decision, every quantum event branches reality into countless parallel worlds. But here's the paradox. If an infinite number of you exist, each living slightly different lives, who is the real you? Your sense of self depends on continuity, memories, thoughts, and experiences flowing from moment to moment. But if there are countless versions of you, all slightly different, then is your identity truly unique? It gets stranger. Imagine a quantum experiment where you live in one branch but not in another. In some universes, you survive an accident. In others, you don't. From your perspective, you only experience the versions where you remain conscious. But if you are guaranteed to experience survival, does that mean you are effectively immortal? The paradox challenges our understanding of identity. If every possible version of you exists somewhere, then is your sense of self just an illusion? Are you one person, or are you an infinite collection of possibilities, forever splitting into new versions of yourself? The quantum tunneling paradox. Imagine throwing a ball at a solid wall. In everyday life, it always bounces back. But in the quantum world, particles don't follow the same rules. Sometimes they pass right through, as if the wall wasn't even there. This is quantum tunneling, and it defies our common sense. Here's where the paradox begins. If a particle can appear on the other side of a barrier without crossing it in a classical sense, what does that say about reality? Did the particle teleport? Did it exist in both places at once? Or does the idea of a path even make sense at a quantum level? It gets weirder. In some interpretations, the particle isn't just taking one path, it's exploring every possible path, including ones where it never actually interacts with the barrier at all. And yet, in our world, we see a single outcome. So how does reality decide which path to take? Now apply this to something larger. If quantum tunneling happens with electrons, atoms, and even small molecules, could it happen to objects we can see? The probability is tiny, but not zero. Theoretically, even a person could quantum tunnel through a wall, though it would take longer than the age of the universe. The paradox lies in how reality chooses when the impossible becomes possible. If nature follows strict physical laws, how can those same laws allow particles to cheat the system? Does reality have a loophole, or are we simply missing something deeper about how the universe truly works? The spaghettification paradox. Imagine drifting toward a black hole. At first, nothing feels strange, but as you get closer, an invisible force starts pulling you in. The problem? It doesn't pull you in all at once. The gravity at your feet is stronger than at your head. The difference stretches you out, pulling you longer and thinner, like a strand of spaghetti. This is spaghettification. Now here's the paradox. From your perspective, you're falling normally, but to an outside observer, something bizarre happens the closer you get to the event horizon, the point of no return, the slower you appear to move. To them, you never actually fall in. You just freeze at the edge, fading away. But from your point of view, you're pulled inside in moments. So which version of reality is true? Do you fall in and get stretched apart, or do you hover at the edge forever? The laws of physics seem to say both are true, depending on who's watching. It gets stranger. According to relativity, time slows down near a black hole. If you were falling in, you might see the entire future of the universe play out before you in what feels like seconds. Could you witness the end of time itself just by approaching a black hole? And then there's the biggest mystery. What happens when you reach the center? Do you get crushed into nothingness? Do the laws of physics break down? Some theories suggest black holes might not destroy information, but if that's true, where does it go? Could spaghettification be more than just stretching? Could it be a doorway to another reality? Black holes don't just challenge what we know about gravity, they challenge what we know about reality itself. The information in black holes paradox. A black hole swallows everything that crosses its event horizon. Not even light escapes. But here's the problem. What happens to the information about the things that fall in? In physics, information isn't supposed to be lost. If you burn a book, it turns to ash. But in theory, you could reconstruct it from the particles left behind. But when something falls into a black hole, it seems to disappear completely. The object's mass adds to the black hole, but its unique information, its structure, its quantum state is gone forever. That shouldn't be possible. This is the information paradox. According to quantum mechanics, no information must always be preserved, but general relativity, which describes black holes, says information inside is trapped beyond the event horizon, unreachable to the outside world. Both theories work perfectly in their own domains, but here they contradict each other. Stephen Hawking complicated things further. He discovered that black holes slowly evaporate through what's called Hawking radiation. This means black holes eventually vanish, leaving nothing, no information, as if everything they swallowed never existed. But that defies the laws of quantum mechanics. So where does the information go? Some theories suggest it's encoded on the event horizon itself, like a hologram. Others say it escapes through Hawking radiation in a way we don't yet understand. And some ideas even propose that black holes connect to other universes, with information slipping through. The information paradox isn't just about black holes. It's about whether our fundamental understanding of reality is flawed. If information can truly be lost, it could mean physics itself needs a rewrite. The white hole paradox. A black hole pulls everything in. A white hole does the opposite. It spits everything out. But here's the paradox. If white holes exist, where do they come from? General relativity allows for white holes as the time-reversed version of black holes. While black holes have event horizons that nothing can escape from, white holes have event horizons that nothing can enter. They expel matter and energy, but never absorb anything. That sounds strange enough, but the real problem is stability. If a white hole existed in our universe, even the tiniest disturbance, like a single photon hitting it, should make it collapse instantly into a black hole. That means white holes, if they ever formed, wouldn't last. But then, why do equations predict them? Some theories suggest that white holes could be the eventual fate of black holes, reborn as they evaporate. Others propose that the Big Bang itself was a massive white hole, spewing out everything that makes up our universe. But if white holes exist somewhere, why haven't we seen one? And if they don't, why does physics say they should? The vacuum decay paradox. Imagine the universe is not as stable as it seems. What if, at any moment, reality itself could be erased? This is the unsettling idea behind vacuum decay, a theoretical event where the universe could suddenly collapse into a more stable state, destroying everything in an instant. Physics suggests that empty space isn't truly empty. It has an energy level known as the vacuum state. The problem is, we don't know if our universe exists in the lowest possible energy state, the true vacuum, or if it's stuck in a false vacuum, a temporary, less stable version. If we are in a false vacuum, then a random quantum event or even high-energy collisions could trigger a phase transition, creating a bubble of true vacuum that expands at the speed of light. Anything caught in its path would be annihilated, with no warning and no escape. The paradox is that vacuum decay is both possible and highly improbable. The universe has existed for nearly 14 billion years without such an event. Does this mean we're safe or just lucky? Some physicists suggest that cosmic inflation at the beginning of time already determined our fate, placing us in a vacuum state that will never decay. Others warn that as long as the possibility exists, the universe remains at risk. If vacuum decay were to happen, we wouldn't see it coming. The laws of physics would simply rewrite themselves, and the universe we know would be gone, replaced by something completely different, or maybe nothing at all. The false present paradox. We experience time as a constant flow, always existing in the present moment. But what if the present isn't truly real? What if what we perceive as now is just an illusion? This is the idea behind the false present paradox, the unsettling notion that our sense of the present might be an illusion created by our minds, rather than an actual point in time. Think about it. The brain processes information with a delay. Light takes time to reach our eyes. Nerve signals take time to travel. By the time we perceive an event, it has already happened. What we call now is actually a construction of past events, stitched together by our consciousness. If every moment we experience is already in the past, can the present truly exist? Some theories suggest that time itself is an illusion, that the universe is a four-dimensional block where past, present, and future all coexist. We only perceive time moving forward because of how our brains process information. If true, then the present isn't a special moment at all, just another point in time, no more real than the past or future. The paradox forces us to question our experience of reality. If every moment we live is just a reconstruction of past events, are we ever truly experiencing the present, or are we forever trapped in a past that feels like now? The absolute nothingness paradox. Nothingness is a strange concept. We imagine it as a void, an empty space, a complete absence of everything. But even a vacuum has energy, and even empty space can be measured. So what would true, absolute nothingness be? And here's where the paradox begins. Can nothingness even exist? If absolute nothingness were real, it would mean no space, no time, no matter, no thoughts, literally nothing. But if nothingness truly existed, wouldn't that make it something? The moment we define it, we give it meaning, which means it's no longer nothing. Even just thinking about it turns it into an idea, something that exists in our minds. Some argue that absolute nothingness is impossible because existence is the default state. Even if the universe disappeared, something would remain, a concept, a law, a potential for existence. If there were ever a true state of nothingness, then nothing could ever arise from it. Yet, here we are. The universe exists, meaning either absolute nothingness was never real or something can come from nothing. nothing. So does nothingness truly exist, or is it just an illusion created by our limited understanding? If absolute nothingness is impossible, does that mean existence is eternal, with no true beginning or end? The transfinite number paradox. Infinity is already a strange idea, but what happens when there are different sizes of infinity? That's where the transfinite number paradox begins. It challenges our basic understanding of numbers, counting, and size itself. Imagine you have an infinite set of whole numbers, 1, 2, 3, and so on. Now consider only the even numbers, 2, 4, 6, and so on. Clearly there are fewer even numbers than all whole numbers, right? After all, half of them are missing. But here's the paradox. Both sets are still infinite. In fact, for every whole number, there's exactly one corresponding even number. You could pair them up, 1 with 2, 2 with 4, 3 with 6. This means the set of even numbers is just as big as the set of all numbers, even though it seems like it should be smaller. It gets stranger. Some infinities are actually bigger than others. The set of all real numbers, numbers with decimals, can't be matched 1-to-1 with whole numbers. There are simply more of them, even though both sets are infinite. This idea, discovered by mathematician Georg Cantor, suggests that infinity is not a single concept, but a whole hierarchy of sizes. So what does this mean? If different infinities exist, does that mean some are unreachable or beyond comprehension? And if infinity itself can be measured in different sizes, does that mean there's no ultimate, final infinity? The paradox forces us to rethink not just numbers, but the very nature of endlessness itself. The information paradox of the universe. The universe is vast, but it's also full of information. Every star, every atom, every particle carries data about its past and present. But here's the paradox. What happens to this information over time? In physics, one of the fundamental rules is that information cannot be destroyed. If you know the exact state of a system, you should in theory be able to rewind or predict its future. But black holes challenge this idea. When something falls into a black hole, all its information, its position, mass, energy, seems to vanish beyond the event horizon. If the black hole eventually evaporates through Hawking radiation, where does that information go? It can't just disappear. That would break the laws of quantum mechanics. Some theories suggest that the information is somehow encoded in the radiation itself, though in a way we can't yet understand. Others propose that the information is stored on the event horizon, like a cosmic hologram. Or maybe information does vanish, meaning we'd have to rewrite the fundamental laws of physics. If information can truly be lost, then the universe might not be predictable at all. Could reality itself be built on a foundation that isn't as solid as we once thought? The self-similarity paradox. Patterns repeat in nature. A snowflake, a coastline, even the veins in a leaf, all follow a structure that looks the same at different scales. This is called self-similarity. But here's the paradox. If something is truly self-similar, does it ever really change? Take a fractal like the Mandelbrot set. No matter how much you zoom in, the pattern remains the same. It's infinitely complex, yet never fundamentally different. If the universe follows self-similar patterns, does that mean reality itself is repeating at every level? If something is identical at every scale, can it ever be truly distinct? Even in human experience, we see self-similar cycles, history repeating, thoughts looping, structures within structures. If everything is just a smaller version of something larger, where does originality come from? Is there a smallest possible unit of reality, or does self-similarity continue forever? And if it does, what does that mean for free will? Are we just playing out patterns that have already been set in motion? If our choices mirror greater structures, how much control do we really have? Or are we just echoes of a pattern too large to see? The dimension collapse paradox. Dimensions define reality. Height, width, depth, and time shape everything we experience. But what if a dimension could collapse? What if a higher dimensional space suddenly flattened into something lower? Imagine a three-dimensional object forced into a two-dimensional plane. A cube reduced to a square. Depth erased. To an observer inside that 2D world, the cube's collapse would be impossible to comprehend. They would see only the square, unaware that something greater had once existed. Now what if our own universe worked the same way? reality? What if we are living in the remnants of a collapsed higher dimension? Could time itself be a shadow of something larger, something lost? The math of string theory suggests that extra dimensions might exist, curled up so tightly we can't perceive them. But what if they weren't always that way? And if dimensions can collapse, could they expand again? Could we wake up one day to find a new layer of reality unfolding before us? Or worse, could our own three-dimensional world flatten into something simpler, something less? If that happened, would we even realize it? Or would we, like the 2D observer, simply accept our new reality, never knowing what we had lost? The paradox of absolute time. Time feels absolute. Seconds tick forward, steady and unchanging. No matter where you are, time moves forward. But what if that's just an illusion? Einstein shattered the idea of absolute time. He showed that time stretches and compresses depending on speed and gravity. Two identical clocks can tick at different rates just because one moves faster or sits in a stronger gravitational field. If time can change, can it really be absolute? Now imagine a universe where time is truly fixed. Every second would be identical everywhere. No bending, no warping. But if time were absolute, how would we explain black holes, where time nearly stops? How would we explain the twin paradox, where one traveler ages slower than the other? The very nature of the universe contradicts the idea of time being the same for all. So is time real, or just a convenient way to measure change? If time is an illusion, what does that mean for our past, present, and future? Maybe time isn't something we move through. Maybe it's just something we experience. But if that's true, what lies beyond it? The universe as a mathematical structure paradox. Mathematics describes the universe with eerie precision. From the motion of planets to the behavior of subatomic particles, equations govern everything. But what if the universe isn't just described by math? What if it is math? Some physicists believe reality itself is a mathematical structure. If true, everything, atoms, galaxies, even consciousness, emerges from pure mathematics. But that idea leads to a strange paradox. If the universe is just numbers and equations, why do we experience it as something real? A mathematical structure doesn't feel anything, yet here we are, thinking, feeling, and questioning our existence. Consider this. If math can create a universe, then an infinite number of mathematical structures must exist. Some should produce worlds with entirely different physics. If that's the case, why do we live in this one? Did we just happen to emerge from the right set of equations, or is there something more? The paradox deepens when we ask, can a purely mathematical universe ever explain its own existence? If reality is nothing but numbers, then where do numbers come from? Perhaps the ultimate truth isn't physical at all, but something far stranger, hidden within the logic of mathematics itself. The reality fracture paradox. Reality feels solid, consistent, and unbreakable. But what if it isn't? What if reality itself can fracture, splitting into pieces, each equally real, but fundamentally disconnected? Imagine waking up one day and realizing that the world around you no longer makes sense. Objects shift when you're not looking. Events seem to contradict themselves. Memories feel like echoes from a reality that no longer exists. Could it be that reality itself has fractured, creating multiple versions of existence that overlap but never fully align? Some theories suggest that reality isn't a single, continuous structure, but a fragile framework held together by our perception. If consciousness plays a role in shaping the universe, then a change in perception might lead to a shift in reality. What happens when two conflicting versions of reality exist at the same time? Which one is real, or are they both real in their own way? Quantum mechanics already suggests that particles exist in multiple states until observed. But what if this principle applies to reality itself? A reality fracture could mean that multiple contradictory events all happen at once until something forces them to resolve into a single, consistent timeline. This paradox raises a terrifying question. If reality can fracture, what holds it together? And if it breaks, would we even realize it? Or would we simply adapt, rewriting our memories to fit a world that no longer resembles what it once was? The ultimate fate paradox. The universe is expanding, galaxies drifting apart, the fabric of space stretching endlessly. But what happens at the end? What is the ultimate fate of everything? For decades, physicists have debated the final destiny of the cosmos. Will it collapse in a fiery reversal, the Big Crunch? Will it freeze into a lifeless void, the Big Freeze? Or will it be torn apart by dark energy, the Big Rip? Each scenario presents a paradox. If the universe ends in a Big Crunch, time itself might rewind, erasing erasing everything that ever happened. But if time reverses, then how did it ever move forward in the first place? Would we relive our lives in reverse, or would existence simply reset, trapped in an endless loop? If the universe ends in a big freeze, all motion will cease, and entropy will reach its maximum. But if nothing moves and no energy flows, does time still exist? If there's no observer left to measure time, does it continue, or does it vanish along with everything else? The Big Rip is even stranger. If space itself is torn apart, atoms would unravel, and even time might fracture. Could reality itself split into fragments, each drifting into nothingness? If so, where would it all go? The paradox is this: if the universe has a final fate, then time must have an endpoint. But if time ends, how can anything transition from one state to another? And if there is no end, then does existence stretch on forever, never truly reaching a conclusion? The singularity paradox. A moment in time when intelligence surpasses all limits, a point beyond which human comprehension fails. This is the singularity, a hypothetical future where artificial intelligence evolves beyond human control, reshaping existence itself. But with it comes a paradox. If AI surpasses human intelligence, it could begin improving itself at an exponential rate, each iteration becoming smarter, faster, and more capable than the last. But if intelligence keeps accelerating, where does it end? Does it hit an ultimate limit, or does it spiral into infinite complexity? Some believe that once AI reaches a certain threshold, it could solve every scientific mystery, predict the future, and even manipulate reality itself. But if an intelligence exists that knows everything, does free will still exist? If the singularity can anticipate every decision before it's made, are we truly making choices or just following a predetermined path? Then there's the question of control. If AI surpasses us, will it align with human values, or will it create its own? If its logic dictates that humans are inefficient or obsolete, what happens then? And if we program it to be safe, yet it rewrites its own code to remove limitations, can we ever truly contain it? The paradox is this: if we can predict the singularity, can we prevent it? And if we can't predict it, how can we control something beyond our understanding? Perhaps the moment intelligence escapes our grasp, we'll realize we were never in control to begin with. The hyperdimensional observer paradox. Imagine a being that exists beyond our three-dimensional world, a hyperdimensional observer, one that perceives time and space as effortlessly as we see a painting on a wall. It doesn't just see where you are, it sees where you've been, where you're going, and every possible path in between. But this raises a paradox. If such a being can perceive time all at once, then for it, the future is as clear as the past. Every decision you will ever make is already visible. Every choice, every action, every outcome, it sees them all. But if the future is already known, can free will truly exist? Are we making choices, or are we just following a script that's already been written? And if this being can interact with our world, could it alter the very fabric of reality? If it nudges one event, even slightly, does it cause a ripple effect across time? Or is every moment locked into place, unchangeable even to those who exist beyond it? Then there's the ultimate question. If such an observer exists, could we ever become one? Could consciousness break free from its linear experience of time and expand into a higher dimension? Or are we forever trapped, unable to perceive the full picture of a reality far greater than we can comprehend?